Viju, we can wait for few more minutes. Okay, you can. Yeah. Very good morning to all. So welcome back to day two session of a 5 days FDP cum workshop on contemporary image processing and cybersecurity application. Today, the first session is handled by Dr. Pradeep Kumar Chaudhary. He works as a postdoctoral fellow at Mayo Clinic in Rochester, Minnesota, within the Department of Physiological and Biomedical Engineering. He earned his B degree in Electrical and Electronics Engineering from Rajiv Gandhi Technological University, Bhopal. Subsequently, he completed his MTech degree in Electrical Engineering at NIT Hamirpur. Later on, he obtained his PhD in Electrical Engineering from IIT Indoor. His research interest or encompasses medical image processing, pattern recognition, machine learning, and ultrasound imaging. So, welcome you, sir.
Thank you. Thank you. Thank you for the introduction. So I'm sharing the screen now.
Yes.
I think the screen is visible now.
Yes, sir.
Okay. Oh, good morning, everyone. So today I'm going to present a topic called uh, the presentation topic is Fourier-Béchel series expansion for medical image processing. So briefly, I will discuss what is Fourier-Béchel series expansion, motivation behind using this type of expansion, and there are total 5 methods which has been developed based on Fourier-Béchel series expansion, and we have used those Fourier-Béchel series expansion for different type of biomedical disease diagnosis. So first one is the dyadic decomposition, which is similar to discrete wavelet transform and wavelet packet transform. Similarly, there was another transform called flexible analytical wavelet transform, where we can vary the Q factor of that. We have converted those Fourier transform based flexible analytic wavelet transform in Fourier Béchel transform. Similarly, we have developed empirical wavelet transform based on Fourier Béchel spectrum and use it for glaucoma decomposition the diagnosis. And then we have used for breast cancer diagnosis, both using mammogram and with a sonographic image. And we'll discuss about brief advantages of this method and how this can be used in future, means what development can be done in this area, and then followed by references. So the first thing we should know that why we require signal representation, because whenever we have to analyze some signal, we have to uh, first convert into something called, which we know early. Like in Fourier transform, we know that we know sine signal, cosine signal. So we convert any unknown signal in terms of sine and cosine so that we can easily understand or analyze those type of signal. So this is the primary reason why we use signal representation techniques, so that we can analyze them. And while analyzing or while using the basis function, means sine and cosine are type of basis function which we use to represent those signals. So it is a well-known fact that if you want to represent any particular signal, it is good to select a basis function which is similar to the signal which we are going to analyze. Means if it is a stationary signal, our sine and cosine functions are best to represent that, but all the real world signals are not non-stationary in nature. So there are many other basis function. It's better to represent them with a known stationary signals. Better example of is that if you want to represent any point in a space, it is better to use Cartesian coordinate instead of sine and cosine function, because that point can be easily represented in x, y, and z coordinate. This whole presentation is based on Fourier Bessel transform. So first I will discuss from where this Fourier Bessel function come into the literature. So the first time this Fourier Bessel or Bessel functions come into literature is when there was an analysis of planetary motion, and by solving that planetary motion, the second order differential equation has been arrived, which is shown in equation 1. So while solving this equation, so there was a scientist called Bessel. He has solved this equation and they got the solution. So the function, the solution of this equation 1 is shown in equation 2, where JV and YV are the Bessel function, and C1 and C2 are the arbitrary constants. And another property is required for any function to be considered as basis function is that they should be orthogonal to each other. That is, when it is a product, when we do the dot product with itself only, we'll get 1, otherwise we will get 0. So the Bessel function of this JV and YV, as I discussed, that it is a kind 1 Bessel function and it is kind 2 Bessel function. So the kind 1 Bessel function follows the orthogonality property. So this JV function can be used for representing any arbitrary function or arbitrary signal in terms of this Bessel functions. So to represent how Bessel function looks like, I have shown this in figure 1. This is a Bessel function of order 0 and order 1. We can see that it is type of a sine and cosine, but decaying in nature. That is, has the property of like a complex or like a sine or cosine function, but with a decaying in nature, which we can say that it is like a non-stationary signal. So we can easily represent them with such type of Bessel function or basis functions. So similar to Fourier transform, the analysis and synthetic equation can be represented as given in equation 4 and 5. The 4 represent the synthesis equation and 5 represents the analysis equation. And this constant is actually a normalization function to make it orthonormal. So similar to Fourier transform, we can also convert Fourier Bessel function into 2D Fourier Bessel function. Means if we want to analyze any image, so we can do it using applying the 1D Fourier Bessel function row-wise followed by column-wise, as we do in Fourier transform, that we apply Fourier transform row-wise to each rows of the image and then followed by column-wise. So if we have to compare that how Fourier Bessel series expansion is better than Fourier transform, it is better. It is required that we can do one-on-one mapping between frequency domain and order domain. And many of the frequency filter banks has been, which is well developed in the literature. It is required that we should convert the obtained information, and if we want to compare that in the frequency with the Fourier transform, we require to convert them into frequency spectrum. So there is a relation called this is a relation which shows that by which we can we can map frequency axis by Fourier Bessel axis. So the zeta k represents the positive roots of the Bessel function, and mu k represents the continuous frequency of that, and L is the length of the signal which is under consideration, and F is the sample frequency. So before going through this, I want to just say that the Bessel function is follow the orthogonality property at their zero crossing point, where zeta m represent the mth zero crossing point of this function, and it is approximately, we can say that each consecutive zero crossing has a difference of pi, approximately pi, not pi. So we can say that this relation, by this we can get that any relation can be considered as of approximately equal to k pi. Means for the, if you know the first zero crossing point, we can easily find further other zero crossing points. So for image processing, generally we consider sampling frequency as 1 as a normalizing term. So we can simplify that term into equation 10. The equation that can be easily simplified in terms of equation 10. So why it is required that we already have Fourier transform, why we have to go to Fourier Bessel series expansion? There are few advantages which we found out that we can choose FBSC as an alternative of Fourier transform. So we have considered any non-stationary signal, which is shown in figure A, and we have shown the spectrum. This is the magnitude spectrum of the Fourier transform. This is a Fourier Bessel series expansion. This is a coefficient and this is the magnitude of that. So we can see that if the signal length is of 50, then we will get total 50 FBSC Fourier transform coefficients, and similarly we'll get 50 FBSC coefficient. The difference here is that there is due to conjugate symmetry property of Fourier transform, after 25 we will get the mirror image of the positive frequency components, which is not here in C. So if we have to separate out, we can see that if we'll apply some averaging filter to this, so these two component will merge to each other. So we will not able to segment out this two frequency component easily. Whereas when we analyze this, so we can easily segment out two frequency component from the spectrum. So if wherever we have to filter out the mono components from the signal, we can easily do that. Also in Fourier transform, we know that we have both since it give for a real signal, it gives complex representation. So the memory requirement is also more, whereas we just have only for positive, we have just only a magnitude or amplitude value. We do not have any phase information in that. So if we, this can be considered as one of the drawback also. Whenever we have to do for phase analysis, we have to apply Hilbert transform to the given signal in order to get the phase information. So similarly, now with this spectrum, we can also see that whenever we have to design a filter bank, we have to design a filter bank for both positive frequency whereas negative frequency, which we have to, whereas in case of Fourier Bessel transform, we do not have to consider any negative frequencies, which is intuitively easy to implement anything. Means if we have to design a filter bank and have to perform some filtering, it is very easy understandable. So filter bank design is not that complex. This is like, as I told earlier that while representing any signal, it is considered that we have to choose the basis function based on the signal which is under analysis. So all the real world signal are like this is an amplitude modulated signal, and this is a Fourier transform of that, and this is a Fourier Bessel representation of that. So we can see that there is a band of frequency in Fourier transform. So more number of coefficients values has been obtained, whereas we just get one peak at 1/50th value. So very compact representation can be obtained. So whenever we have to perform like a compression like DCT is also follow the same property as Fourier Bessel transform, that only provide positive frequencies, or there's no complex information in that. So so this can be used for just like a JPEG compression also. We can use this property and convert for use for image compression also. So the first method which I'm going to illustrate here is Fourier Bessel dyadic decomposition and Fourier Bessel exponential based. Uh, Both are actually a dyadic decomposition method. One is the based on when we go on dyadic decomposing in lower frequency band, whereas there is wavelet-Peclet transform. We know that we perform dyadic decomposition both in higher frequency and lower frequency. So what is the advantage of FBAC instead of using Fourier transform here or wavelet transform here is that we can get one extra level of decomposition. The reason behind I'll discuss this shortly, and also that we can get any level of decomposition in discrete wavelet transform. If we want a particular subband, we have to go on decomposing step by steps, whereas in FBAC there is the advantage that we can do it by using just single steps. The reason for that I can explain it like this. You can see this spectrum. This look like a sinusoidal signal, and when we convolve this, consider an example. We have a sinusoidal signal, and we are convolving with a Gaussian function. So it look like that that there is decaying in nature. So we can say like that it is like performing, there's a sudden break, which what we call ringing effect. We use a rectangular window. Whenever we use a rectangular window, there is a ringing effect. So that can be reduced using when we use we can do rectangular filtering in this type of transform, because there is no sudden break or drop in the there's no ringing effect in such type of transform. So as I told you that we can get one extra level of decomposition. Reason behind is that that we know that in Fourier transform we have n/2 unique coefficients, because from n/2 plus 1 to n we have repeated coefficients. So whenever we use order spectrum, we have n unique coefficients. So more level of decomposition means, suppose it go for n level of decomposition, we want get one extra level of decomposition. So we go for better pyramid based analysis, or deeper frequency analysis can be done using order axis. Same we will see in wavelet packet transform. We know that discrete wavelet transform perform dyadic decomposition only in low frequency bands. In this spectrum, I've shown L as a low band, and H represent the high pass band. And here same is in this case. The only difference in wavelet packet is that we do the same dielectric decomposition high frequency also. So what we have done is that we have taken a chest X-ray image, chest CT images. We have pre-processed it, taken negative of the chest X-ray image so as to enhance the fume present in the X-ray images. We apply this type of decomposition. After decomposing them into components, we have applied, we named it as subband images, which is abbreviated as SBIs, and then each subband images has been passed to pre-10 network individually, and through the last fully connected layer, we have assembled all the features, and then through any type of classifier, we can classify them into. So this application has been used for COVID-19 diagnosis, pneumonia diagnosis. So we just have to pass it to classifier, and it will give the performance based on the feature which we acquire using CNN. So for that, we have used two databases, one for chest X-ray images and other for chest CTI images. So these are the images which we obtain after decomposition. So we found that when there is a patient suffer with the COVID-19, they show the symptoms like pneumonia. So the fume is distributed throughout the lungs, whereas there is patches of fumes present in normal pneumonia. So there can be variation. So depending upon the model, how it is, and about what type of images at what stage of pneumonia we are getting, the performance can vary. So the first component, the first represent the COVID-19 subject, pneumonia subject, and normal subject. And this is the approximate component. This is the detailed component of that, which generally contain the edge information present in the normal images. Similarly, this is actually when we have used dyadic decomposition. There is counterpart of discrete wavelet transform, and this is when we use the counterpart of wavelet packet decomposition. So in this, we have done the analysis. Means just as I discussed that we have got channels. We named this particular as 1 channel, 2 channel, like that. So we have done analysis for each channel, that which channel has more information, so that we can get find that which subband has more information regarding the white fumes present in that. So we have compare at different level of decomposition. Each channel has been analyzed, and since while analysis we found that for the FDP, this discrete wavelet transform has given best performance with level 1 decomposition. For higher, it doesn't give any good performance. So we have stopped just for level 1, whereas we checked for wavelet packet best Fourier basis expansion for level 1, level 2, and level 3 decomposition. And we found that by fusion, we got for the level 2 decomposition, we are easily able to decompose or classify the chest X-ray images. There was some variation in chest CT images, but we were able to easily classify in chest X-ray images. So we also as we in the framework, as I show that we have used different type of CNN models, pre-10 models, and we found that ResNet 50 has given good performance for both chest X-ray images and chest CT images. And these are the different optimizers which we have used for all 5, and we found that SGD has given best performance compared to Adams and root mean square probe optimizers. And we also vary different type of classifiers, that which classifier can give good performance after fusion operation. So we found that random forest has given comparatively better performance compared to others. So to analyze that, instead of using all subband images, can we select a particular subband which has more information? And as we know that Fourier Bessel has the advantage that we can do direct filtering instead of go step by step decomposition. So we just found that which frequency band can be more informatic. So we found that channel 9, which is a detail component. So last 2 components represent the detail component, and 1, 2 represent the low frequency component. So the first 2 lower decomposition subbands, and last 2 components has given the if we just take those portion, we can easily classify them. We can better classify them. Instead of using all the subbands, we can use just this 4 subband, and we can get the good performance. And we have compared the method at that time, but what were the methods present in the literature, and we found that for chest X-ray image, we have outperformed all the methods, but for this, we have comparative performance with the 10th method. So it was more better accuracy has been obtained afterwards, but at the time the paper was published, we have better performance with the other literature methods. So as we in method 2, we have just improved that dyadic decomposition method because we have no control on the bandwidth of the filter banks. So there's a flexible analytic variable transform. Now instead of having fixed Q value of Q factor, we can vary the Q factor of the filter bank. And I will show that what is the effect of changing the Q factor and how this can be useful for that. So this is that whenever we perform a filtering using filter bank, or if anybody remember that how discrete variable transform work is that if we want to represent the filter bank design, so it look like that there is no third subband, but no third filter banks, but it has first two columns of filter banks which has been used in discrete variable transform. And here A, C, B, D are generally 2 because it's a type of dyadic decomposition. So the dilation values are generally 2 in that case. So now we have to design flexible. We want to flexibility in that. So we make A, B, C, D as arbitrary values, which can be vary according to requirement. So this can be done. This is the process of, or this is a filter bank design for Fourier spectrum. But as we know that for Fourier Béchamel spectrum, we do not have negative frequencies. So automatically we can cut off this part and we will get easy implementation. So by using Fourier Béchamel spectrum, we can get the flexible Q values instead, and also we can compute very easily since we do not have to bother about the negative frequency information. So this is actually here H represent the low pass filter bank, G represent the high pass filter bank. And AB are the dilation factors, which we vary according to that. KP represent the pass band. KP and KS represent, so this range represent the transition band. More than KS represent the stop band. Similarly, for high pass filter bank, and for every cutoff value, there is some constant in order to get perfect reconstruction. So if you want to discover know more about the derivation, how this has been come, you can check the article. So this is actually a perfect reconstruction equation. So to satisfy that our low pass and high pass filter banks that should follow these properties, this constant should be satisfied. And similarly, this is actually the smooth this band, which is called a transition band. To make this smoother, this equation should be satisfied for smooth transition band. So here in this figure, I want to say that what is the effect of Q factor. We can see that if the Q factor is Q factor is equal to 1, 2, 3, 4, 5. So as we go on increasing the Q factor, we can see that we can go for further level of decomposition. Means here this is the lower subband. If we have to again perform a decomposition in this lower subband, we don't have much information left. But when we see at Q factor is equal to 5, even we have more information, we can go for filtering. But by doing higher level of filtering, we can analyze the images or the signal at different frequency scales. So better frequency resolution and better frequency information can be extracted if we have higher Q values. So we have used this filter bank design to analyze and decompose the fundus image. Fundus image is actually a retina image which look like this, and we have used this fundus image to classify them into different grades of diabetic retinopathy and diabetic macular edema. Both diseases are actually caused by diabetes. Diabetes means when the patient is suffering from diabetes, he has to go for regular checkup in order to find that at what stage the person is. And whenever the patient suffers with diabetes, there is a point of time when that person will suffer with diabetic retinopathy, and if it got worsen, there's chances as there will be a diabetic macular edema also. So what happened in diabetic retinopathy is that due to high blood sugar level, there is pressure on the blood vessels. This blood vessel will burst, and there will be release of proteins and lipids, which can be visualized in form of yellow color. And there is burst in blood vessels, so there will be blood flow in the blood hemorrhages in that, which can be shown in figure. Microaneurysm, the small dots, and hemorrhages means collection of many dots. And similarly, there is neovascularization. When there is a pressure, there is formation of new vessels, very small, tiny vessels, which called as neovascularization. So based on this biomarkers, they can be graded into different forms. So I have collected database from 3 publicly available sources, and on the basis of this abnormalities, they can be classified into different grades. And so whenever this exudate or microorganism come into macular region. Macular region is a portion in the retina where there is different type of cones and rods present in that, so that we can get the color information, sharpness information, whatever we see, what is the color of that, how sharpness is that, all that information is abnormalities collected there. There will be a framework which is used for classification or for diagnostic purpose. We have pre-processed it, apply histogram equalization, so that all the images we have got of same histogram. Then we have applied flexible analytic wavelet transform, and we must know that at what level of decomposition we should go for. So we have set a criteria. So select that which level of decomposition we'll go for. We have gone through different type of subband grouping. I'll shortly discuss what is subband grouping, and then we have find the interrelation between the pixels, which we'll call local boundary patterns, and variation between the neighborhood pixels. So those feature has been used for grading. So to select the level of decomposition, we have used energy-based approach. What we have done is that we have taken the energy of lower subband and then take the ratio with the total energy. Whenever the lower subband has energy less than 0.05, means that now there is no much information in the lower frequency band, so there is no use of going for further decomposition. So whenever we found that there is information less than 0.05, we stop the decomposition. And local binary pattern is actually get the values 1001, like pattern will be obtained, and this information will be obtained using the relation or relation between the central pixel. FC represent the central pixel, and FU represent the boundary or the neighborhood component. So depending upon the variation of the neighborhood with respect to center pixel, we can design a pattern in the image. So those pattern can be termed as local binary patterns. So by this we can find out what is the relation between neighborhood pixels, and similarly what is the variation between the neighborhood pixels can be obtained using this relation, where mu represent the mean of the mask which we are using, and FU represent the neighborhood pixels. Generally, we consider the sensitivity and specificity as the parameter for selecting the model, but we know that not always sensitivity means sensitivity indicates that how well we are able to classify the positive class as a positive and negative class as a negative class. So we have used define a parameter which we have taken average of sensitivity and specificity to select that which model is giving best performance. So we have checked for different Q values, means different PQRS values. We found that for P is equals to 1, Q is equals to 2, and an R is equals to 3, we get the better performance. Or this is the type of filter banks. This type of filter bank or Q factor value we require to get the better accuracy for the particular application. So while analysis, we found that there are multiple subbands present in the signals. So as I've shown in chest X-ray images that we go for analyzing each channels. So here we done a different technique. We found that the last subband, there is a fourth subband, is always noisy information. So there is no much information present in that. So we can easily neglect that. Similarly, we found that is 2 and 3. 2 represent the horizontal component of the horizontal detail component and this the vertical detail component. So if we add them, the information which we get is almost the same, but the orientation is different. So just we can add this. So we just analyze that what is the effect of doing this thing. So this is the subband which we obtain. We cannot easily say that what is happening inside that. So just I'm saying that there is a 10 channel decomposition, 7 channel decomposition means 10 channels means I'm considering all subband, 7 channel I'm removing the higher components, and in 4 channel subband diagonal components are added up. So here we can see that if I'm analyzing each channel separately, we can see that the red spots can be easily highlighted in B channel, and yellow spot exit channel can be easily spotted in R channel, and similarly in green channel there's blur of all. So we can get a different type of information, and since we are using the neighborhood based analysis, that is what is the information relation between neighborhood with a central pixel, so this is local boundary pattern, so we'll easily able to classify different type of level of this abnormalities, and we can easily able to diagnose them into different grades. So during the analysis, we have used joint accuracy parameter. Means we will consider the value 1 when we have get a good performance for both diabetic retinopathy and diabetic macular edema, and we will consider as 0 if we'll give false classification for any of the one cases. So by this we can find out how accurately we can grade both both diabetic retinopathy and diabetic macular edema with the same efficacy. And we found that from the literature we got 4% improvement with our proposed approach. So and for Mesido database we have compared with other approaches, we have good approximately outperformed the previous available methods. Now in third approach, we have in the previous two approach we have seen that there was a dyadic decomposition, and in the second method we have used flexibility in the filter banks, but it was not dependent upon the signal. What we have to do is we have to do experiment, and then we have to find at which Q value and which PQRS value we are getting good performance. So we required adaptive decomposition method. So here we have used empirical wavelet transform where filter banks will be designed based on the signals we are giving to it. So and we have used it for glaucoma diagnosis. Here also we have used fundus images. The normal general cause that person suffering with for glaucoma is that due to aging effect, as we go older, there is a blockage or there is a problem in flow of liquid. There is a liquid called aqueous humor which flow within the eyes, and the work of this aqueous humor is to maintain the temperature and lubrication inside the eyes. So due to some aging effect or due to some activity, there is the injury in the eyes, so there is a blockage of the flow which put the pressure on the walls of retina. Due to this pressure, there is cause of fuming at the optical disc region. Optical disc region is a region from where our eyes is connected to brain. So this is optical region. So there is a cupping of that. So this is the clinical task that if the doctor has to classify that person is having glaucoma, they use cup to disc ratio. If it is level, it is above 0.7, it is considered as severe case of glaucoma. So there's many publicly available database. I have used 3 publicly available database. One is called Medical Image Analysis Group. Another one is DrishtiGS, which is our Indian database, and third is Origa database. So to design Fourier-Basel-based empirical wavelet transform, what we have this I consider as the image of size m cross n. We will apply Fourier-Basel series expansion to each rows, and then we add, or we can take an average along each column, and the obtained vector will be our average row spectrum. Similarly, if we do same task column wise, means applying FBSC column wise and taking the average along rows, we will get the average column spectrum. So we have convert 2D images into 1D images. To explain that what is the what is the advantage of using Fourier basis spectrum instead of Fourier transform spectrum, we have taken the row spectrum of these toy images, and we can easily find out that the many components cannot be easily segmented out, but whereas we can here we can easily segment out many frequency component present to that. So if the frequency component very closely spaced and having low amplitude, low energy cannot be segmented out using a Fourier transform, because of low n by 2 unique coefficient, whereas we provide n unique coefficient, so more resolution is there in the spectrum. So we were able to easily segment out the mono component presented there. So based on this mono component, based on these boundaries, now we can design a filter banks. Means the first, the 0 to some particular boundary values, we have a low pass filter banks, and other will be like a stop pass band filter banks will be there. So based on those boundaries, we can design a filter bank. So this is the low pass filter bank, which is initially it will be one, there will be smooth transition, then there will be whole stop band, and all other will be like a band pass filter, having stop band, having a pass band, having a decaying transition, having a rising transition, and the stop band. And this sine and cosine actually a smooth transition, and should follow some constant in order to have smooth transition, and there is no overlapping of passband of two consecutive filter banks. So if you want to go through the mathematics behind, you can go through an article of empirical wavelet transform. We can easily find out. So if we have m boundaries in row spectrum and n boundaries in column spectrum, so total m plus 1 cross n plus 1 subband images will be obtained. So if we'll for example, if we have found only one boundary in row spectrum and one boundary in column spectrum, we will get 4 subband images. So we have given a schematic diagram which we have used here. We have used both a conventional machine learning method and also a CNN based method. So we have taken input image, decomposed into subband images, extracted a texture feature, because the changes which will come in glaucoma is in optical disc region, as we have seen that the cupping is increased in as a person having glaucoma. So the main information is the texture information. So we have analyzed the texture feature at different frequency scale, and once we get the features, we find out which features are contributing more in classification, and those features and then used for any classifier can be used to classify them. And in the CNN based approach, the same concept which we have in chest X-rays application, we have decomposed into subband images. First, when we approximate, other will be detailed components. We apply pre-trained ResNet 50, uh, extract the features from large fully connected layer, ensemble them. Ensemble can be done in various form, like taking the minimum value at each channel, maximum value at each value, or embed it in column wise to get a added feature spectrum. And we can use any type of this softmax layer and then classify them into different categories. So we have also explored a uh, variant of 2D FPS EWT. Means we can also do it in different frequency scales. Means, as we know that most of the information in image is present, or any signal present in low frequency band, so we consider that if what will happen if we'll just use full spectrum, when we use half spectrum, and when we use quarter spectrum. And we have analyzed for different databases, and we found that and we have done for both CNN based approach and with CNN and what were traditional machine learning based approach, and found that our approach has given satisfactory results and can be used for clinical practice as well to assist the doctors. The fourth method is 2D Fourier Bessel decomposition method. Previously, we are using the magnitude spectrum. In this, we have used the phase information. So to consider any signal to be having one frequency component, they should have they should have linearly increasing or linearly decreasing phase. Means if we have to separate out the mono component in terms of phase, there should be a linear phase in that. So on the basis of that property, we just convert FBSE spectrum into complex representation. As I told earlier, that it only provides real coefficients. So what we have done is that we have taken a signal. So what our decomposition method is doing is that we have a signal FM, n can be decomposed into E mono components and residue. And each mono component should follow the orthogonality property. Means when we do the dot product of them, it should come 0. This is the property to consider any monocomponent as a intrinsic band function, and we have named this intrinsic band function as Fourier-based intrinsic band function. So if we want to say that a monocomponent is intrinsic band function, it should follow this property, and should if giving this such type of representation should follow this property. So what we have done is that we have converted our spectrum into complex signal by using Hilbert transform to the original signal, and then add them to get the complex representation. Once we get the complex representation, we can represent them into phase and amplitude. So now so this equation 27 and 28 can be equate to each other, and it can be represented as this. Here I represent the ith monocomponents. So suppose we have to decompose this, remove I terms from it. So I term from it, we can say that is a zt can be represented as ai at e raised to power j phi t, and we have decomposed into I parts. So I such components has been separated out, and so that's why we are using the summation operation. And since we are representing in the spectrum form, we can represent the same thing in the spectrum form. So each I value can be represented using few coefficients value. That is, suppose if I want the first component, I can represent like a1 t e raised to power j1t, and suppose till n1 it follow a phase property, which I said told earlier, that if the phase is constant, we will consider as a say one monocomponent. Once there is a change in phase, means that there's another frequency component is coming in that signal. So based on that relation, we filter out the coefficients value. So suppose for n2 there is, suppose at n1 there is change in phase, so we will stop our coefficient grouping and we'll call it as first subband. Similarly, we'll go from n1 plus 1 to another point called n2, where there is linear increase in phase, so we'll have a second subband. Likewise, we go for higher level, and general representation can be given like this. So how we do is that we go on scanning each phase value of each coefficients and see this relation, change in phase. Once this change in phase is more than 0, we will consider same monocomponent. Suddenly, if we'll see that there is less than 0, means there is change in phase, we'll stop the grouping of the phase coefficients. So by this relation, we can group the coefficients and decompose into various monocomponents. Now, these monocomponents can be non-orthogonal, and as I told you that to consider a subband as an intrinsic band function, they should be orthogonal to each other. So we know in our bachelor courses that when we use Gram-Schmidt operation, we can convert any factors into orthogonal functions. So we use Gram-Schmidt process to make them orthogonal. So whatever operation I've discussed here is can be used for 1D signals, but when we have to perform the same thing in 2D, the same way which I have discussed in empirical wavelet transform, we can do here also. We'll get the average row spectrum, average column spectrum, do scanning of each coefficient and see the property at which the phase value is changing, and we'll separate out the monocomponents in that, and on the basis of that we get the boundary point in both in row spectrum and column spectrum. Suppose M1 boundary is obtained in row spectrum and M2 boundary in column spectrum. So after filtering, we will get M1 plus 1 cross M2 plus 1 subband images, or Fourier-based intrinsic band images. Again, whenever we have to classify benign case and malignant case. Means when there is a person having breast cancer, there can be two type of cancer. One is two type of tumor. One is cancerous tumors, non-cancerous tumor. Cancerous tumors are benign and malignant, and non-cancerous tumor are benign in nature, and we can easily classify them on base of texture and the shape of the lesion. If it is round in shape, well smooth boundary is there, it is generally benign, and having small lesion size, it is benign. And if it is malignant, if it is irregular in shape and there is no smoothness in the lesion, so we will consider as malignant. So again, the texture feature is important to classify them, and all the features which are available in the literature are texture based information. So we have used all the texture information present, well-known texture feature used in this application. We have used all those texture feature with our decomposed level means we are using the well-established texture feature at different frequency scale, and then we have used to check that at what level of decomposition we are getting, means at what number of feature we are getting better performance. So just by 20 features we got the 82.47 performance. Now, while searching the literature, means the performance was not outperforming the various uh, mm, algorithm present in the literature. So we found out that there is a algorithm called uh, feature improvement algorithms. So we merged that algorithm with our approach so as to get the best performance. So what this linear regression based approach does is that we have existing feature space or feature vector. We can use those feature vector and convert into higher dimension by adding non-linearity into that. Suppose we have so what it is does that it uses two parameter called P and Q. P is that how many features, old feature you are using to generate a new features, and Q value is the order value, means what power you want to give to that each feature space. So for example, I'm using two features, means I'm using F1 and F2, maybe F2 and F3, like that two combination of two feature will be used, and Q is equals to 1 means only one power. If I'll give 2 means it will be F1 square, F2 square, like that, means up to that order I can go. So on the basis of this relation, linear operation, this is my randomly I am combining two random features, and we'll create a feature vector, and by this we are linearly multiplying each other. If I want higher order, I can do this operation twice and thrice. And also I can giving a target value, because in the training phase we can give the target values, so our weight will be affected by target value, and that means linear combination will be effect of target value also. So the new feature which space will be weighted based on target values and the linear combination of that. So we have used our old feature and this enhanced feature to classify them. And at p is equal to 6 and q is equals to 2 means 6 feature combination with higher power or up to q, higher of 2 order, we got the best performance. We have compared with different approaches, like when we do not perform a decomposition, we do not do any contrast enhancement, I mean, we do not do pre-processing. When we use order 0 and order 1 2TF base CWT, and we use, instead of Fourier Basel, we use Fourier transform. So we found that just we got better, slightly better performance with Fourier decomposition method. Means they are compatible to each other. We can get better performance with this also. But there is a point of mm, applying different PQ value if how optimizing your optimization you have done. We can do. The idea is to do that how by using same framework or same setup we are getting good performance. So for a particular setup we are getting best performance with our proposed approach. So the previously we have used mammogram images. Here we have used ultrasound images. The use of ultrasound images, that we cannot use mammogram in the adolescent female, because X-ray emit harmful radiation, whereas ultrasound does not use any harmful radiation. So it is better to use ultrasound when we are having a pregnant lady, and and also the image quality when there is uh, for the adolescent moment, the image quality will be improved when we use ultrasound. So here we have used iterative Fourier Basel decomposition method. If you noticed earlier decomposition methods, that the first component is always the approximate component, and approximate component can be obtained by just averaging the original image. So the iterative Fourier transform, or it was not actually the mm, iterative decomposition method. What actually it does is that it uses averaging filter to obtain the approximate subband, and remaining will be considered as the higher frequency band, or the higher detail component. So the idea here is to select the length of the filter bank we get the similar subband as we get in filter bank when we use the frequency based decomposition methods. So there is a relation which we found out, that when there is, suppose at boundary f1 we have some mono component by any criteria. Here we have used empirical wavelet transform based approach to get the boundary that where there is mono component, the same as which we have done in empirical wavelet transform. We compute the boundaries, and once we got the boundaries, we can using the 2 by that f ratio, we can get the length of the average filter bank. We apply the average filter bank to the signal. We get the xn to that. We get the xn signal when we do averaging to fn. We have subtract our the average component to fn, and the signal which will be obtained is considered as IMF, intrinsic mode function. Similarly, we go on for different level at means different level of decomposition, means we iteratively perform the same task at the lower frequency band, and we'll get the different IMFs. And we can do this in images also, as I've by doing that by doing average row spectrum, average column spectrum, and do the same operation, and we can get the subband images. So here we have used CNN based approach, and we have used kernel function. Kernel function is same as we are adding non-linear to the feature space which we are obtained. Previously, we have used linear regression based weighted approach to add the non-linearity into it. Here we have used the well-established SVM based kernel banks, which is RBF, polynomial KF, and LKF, which is generally used in SVM to mm, transform the lower dimension feature space to higher dimensional feature space, so that support vector can easily segment out or separate out the features. So this is, we have used different type of pre-trained network. Again, we got best performance with ResNet 50, and we have used two publicly available database. One is database B and BUSI database, and we got good performance with polynomial kernel function and with random forest classifier. So in conclusion, what I want to say that we see that with our approach in dyadic decomposition, we found that any level of decomposition can be obtained in any level in a single step. Means whatever subband we want, we can get in single step, and also. And also the advantage was that one extra level of decomposition with more multi-resolution analysis can be done using Fourier-Basel spectrum. And flexible analytic wavelet transform is we see that since we get only positive frequencies, so one can easily implement the filter banks in FBSE spectrum. And since we have higher resolutions in FBSE spectrum, so we see in FBSE empirical wavelet transform that the mono components, when the spectrum are closely spaced, we can easily separate out in FBSE spectrum as compared to Fourier transfer spectrum. In FBTM, we get a better performance with the same experimental setup. The reason behind it was that the Bessel function is non-stationary in nature. So intuitively, we can say that it is good to represent non-stationary signal based on that. And similarly, iterative filter bank, it's one of the, since we are going to filtering in, we are getting the boundary in boundary in frequency domain. Means generally it is averaging in means this operation, iterative operation, is done in time domain. So it is easily affected by noise present, because the noise present in the signal is more affected in time domain. So if you analyze anything in frequency domain, we can get the better decomposition compared to time domain, because we can separate out the noise component easily, not easily but comparatively easier than time domain noises. So the difference what we have done is that we have computed the boundary in frequency domain, and on the basis of the boundaries which we have obtained, we have computed the length, that what should be the length of the filter bank, or the length of the filter bank which we are going to apply in time domain. So we have used both frequency information to get the length of that, and our approach will be free from noise. Means and in future work, since I told you that FBS is like a discrete cosine transform, so it can be used in image compression. So similarly, as in Fourier decompose in the method 4. I've shown you that complex FBAC can be a good tool if you want to represent analyze in phase information. So in future we can consider like using the phase. If you want to analyze based on phase, we can use complex FBAC and do the further studies. Similarly, here I have used order 0 Bessel function. In future can be considered to use different order of the Bessel function. And like we know that time frequency analysis is a well established algorithms. So instead of frequency, we can consider a time order spectrum, that, and we can compare that how better performance can be obtained using time domain representation compared to time frequency representation. So these are the references. So thank you. If you have any questions, you can ask. Hello.
Sir. Yes, sir.
So I have done the presentation.
Yes, sir.
Yes.
Yeah. Any questions from audience side? Yeah. If no more questions, yeah, fine.
Sir,
Yeah,
thank you so
Santosh
much,
sir,
sir.
please.
Thank you so
Thank
much,
you.
sir, on behalf of organizing committee and participants. Sir, once again,
Thank you.
thank you, sir.
Thank you, sir.
Your
Thank you.
any questions? We truly appreciate, sir, for the time and effort you dedicated to preparing and delivering this
Thank you,
presentation.
sir. Thank you for the opportunity, sir.
Thank you so much, sir.
Okay.
Sir, I think no one has any question, I think.
No problem. Thank you.
Okay, thank you so much.
So the participants, the next session will resume at 11:45. We will join at the time. Okay. Yeah. Thank you. Viju?
Okay. Sir, I will start.
Yes, please.
Ladies and gentlemen, it is my honor to introduce Dr. Kishore P. Sarvadekar sir, who joins us today as a distinguished resource person for our workshop. Dr. Kishore P. Sarvadekar sir is working as an associate professor in the Department of Electronics Engineering at IIT BHU, Varanasi. He received his BE degree in Electronics Engineering from KITS COE Kolhapur and the MTech and PhD degree in Microelectronics and VLSI Design from the IIT Kharagpur, India, respectively. He is also a senior member of IEEE. He has about 4 years industry and more than 15 years academic experience. He is the recipient of Vishweshwaraya Young Faculty Fellowship, Ministry of Electronics and Information Technology. So far, 34 MTech and 5 PhD scholars have earned their degrees under his supervision. He has published several research papers in reputed journals like IEEE Transactions, Pattern Recognition Letters, etc. He has published 2 Indian patents also. He has been reviewer for many IEEE transactions and several leading journals of international repute. His research interests includes algorithms and VLSI architecture for image and video processing, image coding system, biomedical image processing, and related VLSI design. Please join me welcoming Dr. Kishore P. Sarvadekar sir. We are privileged to have him here today to share his expertise and insights with us. Sir, over to Kishore sir.
Okay, thank you. So, now
You
let me
can
share.
share the screen, sir.
Yeah, let me share screen. Okay. So I hope my screen is now visible to all.
Yes, sir.
Yes, sir.
Yes.
Thank you very much, Santosh sir, for giving me this opportunity to interact with the audience. And as discussed, my topic of today's talk is on VLSI architectures for image and signal processing. Okay, so typically, uh, if you look at image processing architectures, so I usually keep telling students that there is nothing new in this domain. What we need to understand is the basic digital design. Okay, so everybody studies basic digital design, and if we look at the books available in late 70s, they start with number system, then combinational circuit, logic optimization using KMAP, and combinational circuit like AND gate, OR gate, mux, demux, encoder, decoder. Then there will be latches and flip-flops. And towards the end, you will be seeing the applications of FPGA, flip-flop as shift register, counter, then state machines, and that is the end of the story. Okay. If you open latest book published in this 2023-24 also, it is the same. There is no difference at all. So what has happened is that fundamentals have remained the same. Right. Fundamental remain the same. So where the difference is, but if you look at the uh, gadgets which were available early 1980s, okay, so if you look at 1980s television, it was almost 15 to 20 kg huge box weight. Okay, and today if you look at these screens are less than 2 kg. Okay, 4 kgs flat screen and etc. So the technology, if you look at, there is a drastic change, but the basic fundamental digital design has remained the same. Okay, so what is difference now? How does it correlate? So if you look at the basic building blocks remain the same, and what we have been taught is only basic building blocks like mux, demux, counter, etc. But when it comes to integrate all of them by parts, maybe some counter, some sequence detection, some kind of convolution, okay, then we need to understand which block will be used for what purpose and how to stitch them to obtain a complete system or to obtain a complete system level specification. Okay. And typically what I believe is that in academics, we are missing this link. Okay. We just tell what are the basic building blocks. And what industry is looking for at is how will you use all these blocks to come up with a given system. Okay. So basics to system level. Okay. So that is what is expectation. So if you look at these requirements carefully, it is not that tough at all. Okay, we need to understand a given algorithm. What is the algorithm? Okay, what are the micro steps in between this algorithm, and how to use these fundamental basic blocks to decompose this algorithm and make it realize on a hardware chip so that we will be able to build a chip or integrated circuit out of it. Okay. So when it is a integrated circuit, what happens is that we need to write some code. Okay, and that code, if you look at, there are two different major HDL languages, hardware description languages. One is Verilog, the other is VHDL. Okay, so Verilog and VHDL we have to take into consideration to write this HDL code and build the chip. So when these languages are used, our code should be synthesizable. Okay, synthesizable. So when the code is synthesizable, we call the code is synthesizable when we can create a silicon chip or IC out of the code or functionality written. So this IC can be then plugged in a system to build a system level specification. Okay, is this part clear?
Yes, sir.
Let it be interactive. If you have any doubt, any query at any instance of time, let me
Yes,
know.
yes.
I am not looking at the screen other than this whiteboard. Okay, so if you are having any doubt, you can unmute and you can pause me. Okay,
Yes, sir.
there is no harm at all. Okay, so now when I talk about such a system, okay, maybe we can take a simple algo. Okay, let's say I want to find out sum of first 10 numbers. I varies from maybe 0 to 10. Okay, I am interested in finding summation of this. Okay, so all of us do this kind of experiment in C, MATLAB, Python, whatever higher level languages. Okay, but when I want to create this algorithm on a silicon chip, then we start thinking how it is possible, what should be done. Okay, how do I do it? So we need to start from that perspective. So when it comes to HDL, there is little bit additional overhead onto you as a HDL coder. Okay, so when it is a HDL coder has to first of all think of synthesis. Is the algorithm synthesizable? If yes, then and then only you can build a chip out of this code. Okay, but besides it, what are the requirements? If you look at, there is a timing specification. Okay, so if you want your algorithm to run, you may be expecting the algorithm should run at least at 20 megahertz. Okay. So if it is the case, then when I write this synthesizable code, I need to check either I am really going to achieve this 20 megahertz frequency requirement or not. If not, what is that I need to change in my HDL code so that I will be able to attain the given speed. Okay, so that is one more fact which one HDL coder has to understand. The second fact which HDL coder has to understand is that power consumption. Okay, power. Because today, if you look at the gadgets are power hungry. Okay, because when the speed increases, and if you look at the basic VLSI requirement, if you look at the relationship, switching power as it increases, the power dissipation also increases square proportion. So quadratic relation is there. So as the operating frequency increases, power consumption increases. So if we are looking at the video, which is maybe let it be mobile video, okay. And in mobile video, whatever is the frame rate, maybe 20 frames, 25 frames per second, okay. Each frame in 1 second there are 25 frames to be played, okay. So if you double this, maybe 50 frames per second, your battery will drain very rapidly, okay, because power consumption is directly proportional to speed of switching activity in the given chip. So what we look, if you look at consumer power electronics, consumer electronics, consumers want the data, consumers want the battery to be having long life. Okay. So long life is only possible when we implement a chip in such a way that its original, the given frequencies, for the given frequency, its power consumption is less. So that is other overhead which HDL coder has to think of. The third overhead, okay, as a HDL coder is area. Okay, area of your chip. So area, if it is very large, then what will happen? Your silicon, in case of VLSI industry, silicon is real estate. Okay, direct relationship. So the area increases, real estate cost increases. Chip will become costly. Okay, more the costly chip, less will be the consumers. Okay, not everybody can afford Apple kind of latest Apple series phone. Okay, but if you look at, there is a huge market for Samsung or Oppo kind of, because cost is another factor which is by which the market is driven. So as a HDL coder, one has to think of first of all synthesizable code, then between these three. And typically, this is a golden chord, golden triangle. Okay. If you try to optimize timing, you may increase area or power. Okay. If you try to optimize one thing, other parameters will get pushed. Okay. And our intent should always be to reduce all the three dimensions. Okay. So that is a challenging fact. And that is possible only when we understand the basic HDL or basic building blocks required to implement this code. If we can optimize them at this basic level itself, then we can probably achieve all of these specifications. So that is the meaning. Okay, clear? So now let us look at this basic, okay, basic algorithm. I want to do summation I varies from 0 to 10. Okay. So if you look at the flow chart and all, you can draw, right? So what is basically required? What are the components required for this purpose? That is what we need to understand. So if you look at, I need one adder, okay, to add the given numbers. Okay, so we all study full adder, half adder, okay, then 4-bit adder, and so on. So we know this block. Now what will happen? The adder will have two inputs. Okay. Now how to think of it? Okay. So maybe one input is coming from the user end. I is equal to variable. I 0, 1, 2, 3. Okay. So what should happen? Initially, the adder output should be 0. Summation should be 0, right? So we need to have some mechanism to clear this adder in the initial code. Okay. So what will happen? This sum I can store back as another input here. Okay. So what will happen? I is equal to 0 plus 0. Answer is 0. Okay. Okay. When I varies to 1, then 0 plus 1 and so on. Okay. So this loop will keep on repeating. So now here there is a looping concept. Okay. So now how to realize a loop? To realize a loop, what I need? I need a counter. Okay. So we all know different types of counters: synchronous counter, asynchronous counter, Modian counter, etc. Okay. So adder is required, then counter is required to keep track of how many numbers have been added. And we know when it is a number of first 10 numbers are done, so it means nothing but mod 10 counter. Okay. So we have been already taught mod n counter. Okay. So it is the application of mod n counter. So the moment you are reading one data, counter should keep on incrementing. Okay. So up counter or down counter you can use. Okay. So if it is a down counter, if it is up counter, what will happen? Once one data is fed, count is equal to count plus 1. Then count will keep on increasing. Okay. The moment counter equal to 10, we should generate one terminal count pulse so that we will come to know that the addition is complete and now we want to stop this operation. So maybe we can raise a flag. Okay. That stating that the operation of summation is complete. Okay. So that should be some notification to the user that look, whatever you were seeing, I have performed this operation. Okay. And in between, what should happen? In between, whatever result I am going to get here, those results are invalid. Okay. Because I have not completed all 10 data, right? So I have to have some kind of registering or locking here so that the unwanted data will not be generated at the output. Okay. So now if you look at broadly, what I have done is I have architect this chip. Okay. So the target was to find out summation of first 10 numbers. Okay. And now we are saying that this is your one input. Okay. And these are the outputs. Maybe sum and the other is lecture. And the other is flag, indicating that valid sum is available. Okay. Now, until this flag is not set, we can say that the result is incorrect. Okay. So sometimes we look at the chips, okay, or data sheets wherein it says that the flag, valid flag is not set, the result is incorrect. Okay. So we do have such kind of information provided in the data sheets also. All right. Now, suppose if you don't want to use this flag, okay, only valid answer should be available. Then how can I stop this? So we have to have another way to realize that in hardware. Okay, so how to realize it? So I don't want another output as a flag because maybe I may be having limited number of IO pins on my chip. If it is the case, I should do the rest of the operation internally. So how to do that? It is a simple way. What we have been taught is that we do have something called as a tri-state buffers. Okay. So what will happen? I will use terminal count is equal to 1 as a enable for this tri-state. So as long as 10 numbers are not done, this terminal count pin will be 0. And this tri-state buffer will be disabled. And if it is disabled, the part of input to output, this part is broken. And hence we will not get some output at the output of the chip. Okay. So whenever sum is equal to terminal count is equal to 1, what will happen? This terminal count will be set and there will be a path for this output total sum to the output. And we can tailor its requirement as per our requirement. Tailor the chip as per our requirement. So this is what is nothing but HDL realization. Okay, so this is a simple algorithm and this is how I can realize it on the hardware. Now, when it is to be realized on hardware, what else we need to look at it? Okay, not only this is the logic. This is the building blocks which we want to realize. And we, so far you must have understood that, I know this, I know this, I know this also. So what is left? How to integrate them? Okay. Or how to manage the data path. Now, when I say data path means the internal bus dimensions. Okay, what should be the dimension of this bus? Should it be 3-bit? Should it be 4-bit? Should it be 8-bit? And so on. Okay, so that is what is data path is. Okay, and data path optimization is also important because if you optimize data path, then naturally your switching activity may reduce and power consumption will reduce. Switch data path reduces, number of tracks on chip will reduce, so area will also reduce. Okay, so there is a direct performance relation. So these are the parts which are not taken care of in procedural or higher level languages. Higher level languages. Okay. When you write C++ code or Python code or VB code, Visual Basic, we have never ever thought of how many seconds are required to realize this algorithm or what is the power consumption of this algorithm. Neither we have checked what is the area requirement of this particular algorithm. We are, because this is immaterial for us in the higher level language coding. Okay. Most of the time, what you can check is at the most time requirement. कितने time में मेरा algorithm चलता है. That's it. But for HDL coder, one has to have all these parameters in mind along with synthesizable code. Okay. So now, if I have to optimize this and this, naturally, I have to look at the optimal data path. Okay. So what is data path counting? How to determine it? Okay. So now, let us look at the inner details of this. This is top level understanding of the algorithm and its block. And typically what we call this as in HDL coding is nothing but RTL, register transfer logic or register transfer level logic. Okay, RTL. So now once I know this block, what I need to understand is that what is size of input? Is this input 4-bit, 8-bit? Okay, so when I say 0 to 10, I know the data requirement is 4-bit. 00 to 1010. So it means that this data path is 4 bits. So typically what will happen? I will keep on adding 1, 2, 3, 4, okay. And when it reaches 10, then I may be having summation is equal to whatever is the number. Maybe I assume 10 into 9, 90, maybe 6 or 7 bits. We can find it out later on. Okay. N into n minus 1 divided by 2 or something like that is the formula. Okay. So if I assume that I need 7 bits to obtain the final sum. Okay. So what does it mean? This result may be 7 bit. So here there are 4 bits, but this may require maximum 7 bits to store the value. Okay. If it is the case, it indirectly indicates us that this is 7-bit and 7 bits and 4 bits addition is required. So typically what should happen? This address should be now minimum 6 bits. Okay, because 7th may be the carry. So now I have come to know that what should be the size of adder. It cannot be full adder. It can single bit full adder. It cannot be 4 bit full adder. Rather, it should be 6 bits full adder. Okay, I'm just showing you the example. 6 bits full adder. Okay, so now you have got the answer in other way. So I need to find out these data paths also. Okay, so when it is stated that it should be summation of 0 to 10, so 10 bits, 10 numbers to be counted. So we know that counting 10 is nothing but 4 bits. Okay, so this path should be 4 bit. So now, and this is not 4 bit, this is incrementer. Okay, increment 1 bit. So the moment data is received, increment count value. Okay, so the counter should be 4 bit. 4 bits of counter. And then we need not to generate terminal count 4 bit output. Rather, we want only 1 bit output as a terminal count. So this is how we can realize the data path. Okay. And from here, we can understand exact requirement of my hardware. Okay. Is this part clear?
Yes, sir.
Yeah. So now, once we know this, then coding this is not a big task, because HDL coding, everybody will get this adder code online, counter code online. We need to just modify it, tailor it as per our requirement, and stitch it. Okay. So this is the simplest way to understand algorithm to VLSI architecture or algorithm to chip. Okay. So algorithm to HDL coding. Okay. So this is now suppose if you want this counter to be, now I am considering increment. If you want this counter to be down count, what should be the counter specification? That is what we need to think of. Okay. So if it is a down counter, then we should have a counter which will get initialized to value is equal to 1010. So that on each number, whenever you are reading here, count is equal to count minus 1 should happen. So what will happen naturally when all the numbers are summed, the output will be 0, 0, 0, 0. And then we can say that we can use this OR gate to generate the terminal count pulse. Okay. So when count is equal to 0, generate terminal count. Okay. And on this, now because this is going to produce terminal count is equal to 0, we need to immediately change this to active low tri-state buffer. Okay, so that for rest of the time it will not be sending the garbage data at the output. And that is a small change which one has to take into consideration as per the design philosophy. Okay, so now why I started with this? Because this is typically what you are going to do in image processing. Okay, so when it is an image processing, what happens? It is image is nothing but data arranged in row format. Okay, this data may be 8-bit, 12-bit, depending on the image acquisition system. Okay, so when we perform typical operations like convolution or computing mean or max filter. Okay, so what we need to do is that we need to, usually we form a window of 3x3 size or any odd size, 5x5, 3x3, and then we just look for the numbers in this and perform the operation. Okay, so now Once the operation is performed, we slide this window and we go to the next location and we repeat the operation on the other part here. Okay, so maybe next region is this one. Okay, region of our interest. So it is repeated on this and so on. Okay, so typically this is what usually we do in image. But now what is happening? If you look at this, it was similar to that, but this is 1D, one dimensional. And now when it is an image, we have got two dimensional. One is on the row side, other is on the column side. So data is in two dimensional. So when it is a 1D part is clear, realizing 2D is not that tough. So now what we need to understand here is that how to manage this data. Typically in image processing, the issue is managing the data. So every image is having some pixel information, some pixel data. Okay. Depending on the acquisition system, this data size will vary. Okay. Now, forget about this sliding and all. Okay, sliding architecture, etc., etc. Now let us just assume that I want to do simple averaging of this. Okay, averaging filter or low pass filter. So what is happening if you look at, there is a, I am drawing this part now separately. Okay. So maybe I am having this kind of information stored in my system. Maybe this is row 1, this is row 2, this is row 3. Okay. So this is what is the row 1, row 2 and row 3 information is, which is organized in memory. And when we use higher functions in MATLAB like IMShow and all, we get this array displayed directly on the screen. Okay. So what will happen? Each pixel is nothing but some data stored in this memory. Okay. So now depending on the image size, maybe VG is 640 cross 480. Okay, so we say that it is a VG. What does this indicate? These many rows, these many columns. So I may be having starting from 0 to 639 rows of data. Okay, like this. And 480 is nothing but 0 to 479 such columns or such data values in one row. So we can say that this is our row 0. Okay, so let me relabel this. Row 0, row 1, row 2. Okay. Okay, row 0, row 1 and row 2. So when it is a processor or when some data memory image capturing device will keep on capturing this data. Okay, and then the digitized data will be stored in the memory. Okay, so this will be having 0th row, 0th byte at location. This will be 1, 2, 3, and so on. So finally, depending on the image resolution, whatever is image resolution under consideration, this pixel value will be known to us. Okay. Now, what is the scene on the other row? This will be row 1. Okay, so index number will change to 1. But if you look at this data, this is again arranged in a same way. Okay, 3 and 479. And the story repeats. Okay, for all 439, 639 rows. Okay. So typically if you look at all these are nothing but memories. Okay. And that is why in digital designs, some chapters are dealing with RAM, ROM, PLA, PLDs. Okay. So memory, now what will happen? We need to have a look at this particular structure, how the data is arranged in the given memory. Okay. Maybe this 0 to 479. Okay. There may not be another memory to store this row information from 1 to 79. Okay. So what may happen is that the data, whatever is the data stored in memory, may be arranged in a sequential or contiguous manner. So the first data, so when I will label this as M0, M0 is nothing but this segment. Okay. 0 to 479. Okay. Then the row 2 is nothing but the data which is mentioned in M1. So now because it is a contiguous memory location, so 479 processor will place the next location, next data at 480. 482 now 479. So this will be another 4 480 locations. Okay, so 96, that is 959. Okay, so this will be M1. Okay, so this is the information corresponding to row 0. The next is information corresponding to row 1. Next, and the data will be organized in this way. So 960. 962, next 479, whatever is the number. Okay, so we can find out what is the last address location where this data will be stored. Okay, so definitely this will be at 460 and this will be R3, R2. Okay, and this is M2. Okay, so this is M2. Okay, so now when you look at this structure, what we need to do is that we need to pull the data as per our requirement. Okay. So now if you look at this particular 2D array, what is that we are seeing is I am drawing only first 3 rows of the image now here. Okay, this part. Only this part is now elaborated here. Okay. So this location data is available at 0, 0. Okay, so this is data available at 0th memory location. This data is available at memory addresses. Okay, so I am trying to map memory address. Okay, this data is available at first location. Okay, so 0, then 1, then 2. Okay, because I am using 3x3 kernel, I need to have these 3 data now. Okay, then the subsequent data, this data, we know the offset is 480. So we know that offset is nothing but the last pixel value. So I need to add 480 all the time. So 0 plus 480, I am reaching at this location. Okay, so that is this particular portion. Okay, so this is at 480. Then what is the offset? Add this value plus 480. So that is 481. This is 482 and so on. Now if you look at this location, okay, typically I'll use color palette. Where is that color? Okay, so now when I am interested in this location, third row, 0th pixel. So this is, if you look at one 480, another 480, and then the offset. So that is nothing but 480 plus 480 is nothing but 960. So this is at 960th location. This is at 961th location. This is at 962th location. So to process this 3x3 window, this part, I need 9 pixel values. And those 9 pixel values are stored at 0, 1, 2, 480, 481, 482, 960, 961, 962 memory location of the, in the memory location. Okay, so I need to pull this information from the given memory locations 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and then I need to start processing. And then what will happen? In the next go, when the kernel is sliding, what will happen? This data will go off and another row will come into picture. That will be at 3, this will be at 483, this will be at 963. So offset remains the same. And then I could capture the next window of my operation, which is at this particular location. Okay. Okay. So this is the place where I want to deal with when I am processing at these addresses. So if you look at this requirement, typically, what is that we are trying to do here? We are dealing with a counter. Okay. And the counter should start from 0 and should reach at 479 for this location, to address these locations, right? And to get this, what we need to do? Count value plus 480. Okay. And that is a fixed offset. So we can straightforward write 480 plus count value. Evening. 6:15. 6:15. Okay. So 480, 479. This will keep on changing and automatically this 480 offset will keep on adding. How about the next row? If you look at your requirement, so that indicates us the requirement is at this location is 960, 961, and so on, right? So already I have got 480 here, so I can have one more 480 offset. Okay, and I can say that, hey, whatever is the address output of this should be added with this 480. And then I will be able to point out this location. Okay, so first pointer will be here, 480 differentiated pointer here, another 480, that is 960 pointing at this location. So this is how, once you set the wheel, it will automatically go on because counter will keep on incrementing and this will naturally keep on adding the information. And if you can do this, your kernel will automatically slide. Okay. Is the idea clear? Any doubt in this? Hopefully it is clear to all. Okay. Now, now what will happen? Now, where the problem will occur? This is a contiguous memory. Okay. And now what you are trying to do, see where the problem will come. I'm just showing the first 3 rows of your design. Okay. So this is pointer 1, P1. This is P2, pointer 2. This is pointer 3. Okay. So this is pointing at 0. At that time, this will point at 480 and this will point at 960. And being a contiguous memory, I cannot have 3 address locations to read. Are you getting? Because memory can have only 1 read address. And now I am generating 3 read addresses. So we need to what we need to do? We need to cyclically generate this address, then this address. 1, 2, 3, 1, 2, 3. Okay. So it means that there should be some mechanism to enable one pointer at a time. Okay. So first on reset, when count is equal to 0, this is already there. Then what we can do? We can have one more state machine designed which will keep on saying that P0, P1, P2. P0, P1, P2. Okay. So you generate address, read the data. Then this will give call to the P1 so that you will reach here. Generate the data, send it at the output here. Okay, so memory out. Okay. So second data is also available. So this will send this state machine. So the data is available. Okay. So another 480 offset, it will add, generate the data on the data bus. Work is complete. Now, when you are cycling through this, you need to count is equal to count plus 1. Okay. We need to do this task. And that is what is a state machine. It is clearly visible to you now. Okay. And we have been taught different types of state machine, Millet machine, Murray machine. So we need to realize this, and while changing this state from P2 to P0, we need to perform this additional task. Okay. Then what will happen? Data will be available at the output bus one after another, and we will get 0th location data, 480th location data, 960th location data. Okay. So 2D has come now to 1D. Now what else is required? 9 cross 9, 3 cross 3 kernel means 9 such locations are required. So what will happen? You have obtained this data now and 6 more data to be obtained. So what one should do? You can have now the concept which is taught to you, that is shift register. Okay. So these all are shift registers. And now you start sending the data in this shift register corresponding to R0, R1, R2. Okay. Corresponding to R0, R1 and R2. And this data is now reaching here. So what should happen now? One output to be fed to 3 different outputs. Okay, so what we should do here now, that is what we need to think. How can I do that? Okay, so maybe initially let us say I have got the data at 0th location here, data at 480th location here, and data at 960th location here. Okay, That is what is my expectation is. Okay. But now this is hypothetical. 3 shift registers are there. Shift register 0, SR1, SR2 corresponding to row. Okay. But there is only one line. This line should reach here. How do we do that now? There must be something here. So that is what is a basic digital design course will tell you. Okay, so we need to have a decoder here. A demux, not decoder, demux. So what will happen at the output of this demux? There will be 3 outputs. Okay, so this state machine should also select one of the outputs line here. So what will happen? One data which is selected, when P0, data will go here. When P1, data will go here. When P2, data will go here. And then this will be a common bus which will be serving here. Okay. Or you can have a multiplexer implemented to this. Okay. So demux, mux you can do, or you can just use enable signals to enable shift registers and get the DOS completed. Okay. So this is the another hidden logic or block which is one has to realize. Okay. Is that clear? So now once this is done, when it is cycling from P2 to P0, count is equal to count plus will happen. So what will happen? Pointer will point to count is equal to count plus 1. So it will reach here. Okay, so the moment it reaches here, automatically you are generating 481 and 961 because that is a fixed logic. So now what should happen? When we are generating this, we should also make the shift registers to shift the data. Okay. So what will happen? If it is the case, this 0 will get shifted to next position in the shift register. Okay. So now because of shifting, data available here will be 0. This will be shifted data at 480 and 960. New data will be read, will be from location 1, store it here. Location 481, store it in the another location of the RAM. Okay. So what happened? My device got disconnected. So I'll store it at 481 here and 961 here. So when I'm cycling again, count is equal to count plus 2 will happen. And what should happen now in that case? The data pointer will point to 2. Okay, location number 2. Then automatically you are driven to 482 and 962. Okay, so while you are doing this, again shift this data. Okay, so what will happen effectively? This will get updated. Okay, and the revised information available in the pipe will be 0. Then this will be at 480. This will be at 960. Then this is at 1, 481, 961. This will be 2. This will be 482. And this will be at 962. And you are done, isn't it? If you look at this, your requirement is done. Okay. So now on this kernel, you use this kind of adder. Okay. If you are interested in low pass filtering, so what should happen? So you will do now summation of 9 pixels. Okay. And then you will write back the data to the center pixel. Okay. So for center pixel, now you need to point at this particular location somehow. Okay. And write the updated value. Okay. So this is typically, if you look at what all we used counters, then we used shift registers, then the basic information was available in memory, then some kind of state machine to increment the pointer timely 0, 1, 2. Okay. So 2, that is nothing but 2-bit counter, mod 2, right? And then some decoder or demuxes, okay, to feed the data at the output, okay, or one input, multiple output, so that it will go to shift register 1, shift register 2, and shift register 3. And then you need to find out what should be the sizes of this data path, okay, as like previous case. So here it will be depending on the image acquisition system. This can be 8-bit or 12-bit, okay. Same will be available data here, okay. Now once you got this 9 information, what you can do is you can keep on adding this information, right? Summation 1, 2, 3, 1, 2, 3, 1, 2, 3. So if you look at that particular requirement, so I'll write here now. Okay. So we obtained the data. Now how to perform manipulation, low pass filtering. Okay. So I have got 3 data here. I can use one adder to add this information. Okay. And there can be another adder to add this data. Okay. So whatever operation I am performing on R0 will be performed on R1 as well as R2. So for all those 3 rows, architecture will be the same. So this will be 0, 1, 2. So whatever is the data you have added, similar to that. So I will say that addition of R1. Similar to that, what will happen now? You will get 3 information. Right? Answer from row 0, AR1, row 1, answer from row 2, and answer from summation of row 3. Okay. Or let it be in same notations. Row 0, AR0. Okay. So row 0 का sum, row 1 का sum, and row 2 का sum. So again, these 3 should be added. So the same logic will repeat here also, right? So addition of this and this data has to be added. Okay. But now where the difference will be, depending on your data size here, the data path of these 2 address will be different. Data path here will be +1 because carry will be generated. And this data path, 3 data paths will be the same because pixel size is same. And depending on this, now this will be pixel size +2 because 2 carry may be generated. Okay. Now when you are doing this, the same structure will be there. And now depending on what is the maximum value of sum, these data paths will determine the final value of the final size of the data path for the final sum. Okay, so this is what is low pass filtered sum out of 9 pixels. For the given window, 3 cross 3 kernel, you will get sum generated at this output. Okay, so this is 9 cross 9 filter value sum. Okay. So now, if how to obtain this thing? The way is directly possible to do this. You do these calculations using paper pencil and find out. Or if it is a bigger algorithm, what you can do? You can write MATLAB or higher level languages, code in higher level languages, and then you can look at max on this, max on this. Okay, max mean you can find out. So that will tell you what should be the binary representation for the given max value. Okay, and that binary representation will tell you what should be the data width, data path size. Okay, and then from here you can obtain, okay, I need this block. This should be the minimum size required for my algorithmic implementation. Is the idea clear? Any doubt? Any doubt in this? No. So typically, once you do this operation, what will happen? Now the operations will differ. Maybe here we are doing summation. Okay, now if you want to do average of that, so what should be done? So filtered value, okay. Filtered value, which is 9 cross 9 window. Here, whatever is the answer we have opted. Okay, so this need to be averaged. Okay, averaging filter. So this value, whatever is the answer we have obtained, should be now divided by 9 to obtain the final result. So we can do that part by using a simple piece of hardware. Okay. Maybe you can simply say I am showing it divided by 9. Okay. If you do that, you will get filtered output. Okay. But divided by 9 cannot be realized directly. Okay. So what is possible? Division can be realized using shifters. Okay. So whatever is the filtered value available, if I shift it left 4 times, 3 times, what will happen? When I shift it first time, it will be divided by 2. When I shift it second time, divided by 4. When I shift it divided by third time, it is divided by 8. So instead of divided by 9, I may get divided by 9, divided by 8 value very easily. Okay, and that is why algorithms, when you are realizing in hardware, we need to look at the multiplication, division operations are available in terms of 2 to the power n. Okay. So now divide by 9 is not directly available. Okay. So what one can do, if at all you are interested in this, we need to find out another way. Now what we can do, you can simply look at the output generated by divide by 8 instead of divide by 9. If you use divide by 8, how the output appears? Is it satisfying your requirement? Yes or no? Because in images, majority of time there is a redundancy. Okay. So the output obtained immediately after divide by 8 may be okay to maybe giving the same result for inferences as like divide by 9. If it is the case, then forget about divide by 9 and get the job done with divide by 8 so that your hardware resource requirement will reduce and speed of operation will also be high because it is a shift register. It will be synchronous operation and hence your power consumption, area and speed will be very good. If it is not satisfying your requirement, if you want it to be divided by 9 only, then we need to look at another algorithm or another, sometimes ready-made resources are available to division block on some chips. If it is available, you use it and get the job done. Otherwise, we have to look for division algorithms to implement and get the job done. Okay. So this is moving average. It's nothing but averaging filter in image processing. Averaging filter. Now let us say if you want to do max filter. Max filtering. What will be the change? Max filtering using 3x3 kernel. Now, if you look at the crux will remain the same. Up to this, everything is same. Reading the pixels. Here, we used averaging. That is why we used here adders. Now, we have been asked to find out max. So, we need to find max on each row. So, how to do that? You take a row. Okay. And you apply a max operation, max operator, comparator. Okay. Which one is greater, this or this? Depending on that, you retain the greater number and then again compare it with the third number. Okay. So this will retain the max in a given row. Okay. The same can be realized for other two rows also, right? So wherein you will compare 480th location, 481th location, and 482th location. And the third realization will be comparing data in at location 960, 961, and 962. Okay. So you will get max in each row. Okay. So what will happen? Max in each row can be again compared. Okay, so you can use max comparator. Okay, this will give you max in 9x9 window. If you want the number to be mean, change comparison operation to mean and you will get the filter replaced by mean. Okay. So what is the crux? The crux is how to read the data from the given image data from the given location. And once that is readily available, the filtering algorithm can be changed very easily, and we can get the work done as per our requirement. Okay. So this is in nutshell max or mean filtering. Okay. Now, when it comes to video, video is nothing but video. What will happen? Minimum 25 frames per second. So if you repeat images of given size, 25 images per second, then it is a video. Okay. So what we have done is, we have done the operation so far on a single image on this particular part. Okay. So we need to repeat it for all these 25 frames in 1 second. So it means that our speed of operation should be fast enough so that we can finish this frame, then next frame, then next frame, next frame, and such 25 frames in 1 second. If we are able to do that, is nothing but video processing. Okay. So this is, now look at the requirements. When it is a image processing, whatever this architecture we have seen, the architecture is for one channel. Okay, so typically gray images, if you look at the architectures, this are discussed only for one channel, and we say that gray image. Okay, but if you repeat the given architecture for 3 channels, R, G, and B, R, then G, and B. So whatever is the hardware for this must be the hardware for green, must be the hardware for blue. Okay, so there is no difference at all. That is why nobody discusses video color processing in VLSI. Whatever is this channel hardware, the same channel hardware will be there in G as well as in B. Okay, so if you triplicate the hardware, you are done with color image processing. Color image processing. Okay, and if you repeat it for 25 or whatever is the frame rate given, those many times in 1 second, you are done with video processing. So typically when it is a video processing, it is basically speed of operation. Should be very high. Okay. Now when we have seen this for 3x3 kernel. Okay. So had it be 5x5 kernel, what should be the change? Five cross 5. The change will occur only in the memory read methodology. Here there were 3 pointers. We need 2 more. This state diagram will change to 5 state, P0, P1, P2, P3, P4. Count is equal to count plus will happen from P4 to P0. This will scale up to 5 locations. And because that is 5, this will again 5. This will change to 25. this will change to 5 locations and so on. That is a basic difference when it comes to video processing. Okay, so image algorithm can be mapped, okay, to hardware only when we do have clear-cut understanding of the processes to be performed. Okay, what are the processes? What are the steps to be performed on every data? Okay, if you know that, from there you can find out data path width. From there you can find out how to optimize it. From there you can find out how to reduce power consumption and hence how to improve the speed. Otherwise, you cannot do optimum hardware resource utilization, or it will not be possible to publish your papers in a reputed journal papers. Okay, because it will not be a optimal or up to the mark design. Okay, and hence people will not accept your paper. So you need to improve on all this, then only people will appreciate and accept your paper. Okay. So if you have understood this much, then you can implement any image processing or video processing algorithm without any hesitation. And if you are having any doubts or any queries, now floor is open for we to discuss. Okay, so that's it what I wanted to discuss and deliver in this session. Okay, so now we can have doubt clearing session and such. So 10 minutes are left, and in these 10 minutes I can answer queries if any. Anybody has got any query?
Hello, sir. Can you hear
Yes.
me?
Yeah.
Sir, one doubt is,
Yeah.
shall we convert this video frames to grayscale so that we can process just the grayscale, and then after processing gray, we can convert it back to color. So the hardware requirements will be less. No, just grayscale processing will be there. And also for transmission, we can just transmit these grayscale values. No, we need to transmit the color values.
Mm-hmm. That is possible, but typically people don't do that, because then sometimes if there is a hiccup in conversion, then entire because when it is a commercial product, nobody will take such kind of risk. Okay, because
Like I had tried converting it to gray and then retrieving it back. So the size was very less, but at the same time, the retrieved video was, it gave good similarity. Like when I computed SSIM values, it was giving it was more than 90%. So, but I haven't seen any papers related to this. That's why people are not.
No, that's what I am saying. Commercially, in research papers, people will simply show the information only for single channel, and then they will say that this chip works at this rate, so it is capable of processing these many frames of this size at this rate, and nobody will realize that for all 3 channels. When it is a commercial product, people will think of to optimize the way whatever you have suggested, or they will directly use all 3 color channels and finish the task. So in research papers, nobody will discuss it for color image processing as such. But that is quite possible, converting, because there is a YCRCB conversion, right? Standard.
Yeah.
So one can use that and one can process. Not a harm.
I was trying to, I'm working on data image compression, so, or video compression. So if we convert it to grayscale, then the number of the data bits transmitted will be very less. No, we need to transmit all 3 channels. So that area that I was focusing on, that compression part only.
Yeah, so if you look at the compression, any compression algorithm, initially if you look at, they will convert that RGB to YCRCB.
YCB,
The purpose is that only, to reduce redundancy, to remove the redundancy between these channels. And based on that, there are the quantizer maps, right? Quantization steps. So those quantization steps must be again managed to convert the gray to RGB
color,
and YCRCB and
back
color.
to RGB.
Yeah. So typically that happens. In the standards it is given, but people will not highlight that in the research articles.
Okay. So my aim was to convert to gray and retrieve color from gray back.
Yes.
So that you can reduce the size. But since I have not seen any papers like that related to it, I had a doubt whether this will work out or not.
No, that is quite possible. Can be done.
Okay, sir. Thank you.
Okay.
Any other questions? Anyone? So thank you so much, sir, for your insightful talk. And we truly appreciate, sir, for your time and of effort to dedicate to present here. Once again, thank you, sir, for a contribution, valuable contribution. Sir, we look forward more opportunities to collaborate in the future also, sir.
Sure.
So thank you so much, sir.
Thank you. Yeah.
Thank you, sir. Silambarasan, sir, are you here?
So I'll quit now. Okay.
Yes, sir. Now session is completed. Sir.
I'll leave the meeting. Yeah. Thank you.
Yes, sir. Thank you, sir. Thank you so much. We will start, sir.
Yes, we can.
Yes. Ladies and gentlemen, it is my privilege to introduce Dr. Saptarshi Chatterjee, who joins us today as a distinguished resource person for our workshop on contemporary image processing and cybersecurity applications. Dr. Chatterjee is currently serving as an assistant professor in the Electronics and Communication Engineering Department at the National Institute of Technology, Rourkela. Dr. Saptarshi Chatterjee has completed his PhD from the Electrical Engineering Department, Jadavpur University, Kolkata, India in 2021, and MTech from Department of Applied Physics, University of Kolkata in 2012. Dr. Chatterjee has significant technical research publication in journals and peer-reviewed conferences, and authored one book from academic press elsewhere. He is also the receiver of Vishweshwaraya PhD Fellowship, MEIT, Government of India, and two Best Paper Awards in international conferences. He has received the Outstanding Young Researcher Award in 2021 from IIIT Signal Processing Society, Kolkata chapter, and Outstanding Volunteer Award in 2020 from IEEE Kolkata section. His research initiatives are focused in the area of biomedical signal processing, medical image analysis, artificial intelligence, machine learning, deep learning techniques for condition monitoring of biomedical systems. Please join me in welcoming Dr. Saptarshi Chatterjee. We are privileged to have him here today to share his expertise and insights with us. Sir, you can continue, sir. Thank you, sir.
Yes. Okay. Shall I share my screen?
Yes, sir. You can share 1 minute, sir. You can share, sir, now. It is clear, sir. It is visible.
Okay. Okay, thank you, Professor Santosh, for giving me an opportunity to interact with the faculty members and other participants in this 5-day faculty development program come workshop. It is actually, I am now in Rourkela, so I don't know what is the weather condition in Kottayam, Kerala, but here it is too hot outside. So, but still you are organizing such events for day-to-day regular academic activities is really appreciating. So let me start with my presentation. My today's topic of discussion is medical image analysis towards early diagnosis and monitoring of human disorders. So from the title, you can have an idea that I am going to talk about image analysis, specifically medical images, and the objective is for the early diagnosis and monitoring of different disorders or different human problems, that is. So the problem is that I would like to focus mostly on the two terminologies, that is diagnosis and monitoring. So what is the difference between these two? First, obviously, the diagnosis is to identify the identification of a specific disease, or to identify whether there is any abnormality is there or not in any physiological system of a human body, right? So when there is a term called diagnosis, when we have identified, when we have uh, confirming that disease, we must have a monitoring system. That means we should able to monitor that patient, that how that particular problem is further growing, or how that medications is helping that patient to overcome from that problem. So for that, we obviously need a monitoring system which will um, try to identify, or which will try to observe different parameters, different physiological parameters related to that physiological system. So obviously, when we are talking about this diagnosis and monitoring, there one question of usually comes, that why we the engineers, or we the academicians are more interested to work in this particular field. There are so many emerging fields where we can employ these tools of signal and image analysis, like pattern recognition, computer vision problems, biometric authentications, right, robotics. Many things are there. Among these, one is very important, is the biomedical condition monitoring, and the fundamental is obvious, and image or signal processing. The signal and image maybe differ from different problems for different applications, right? In biomedical condition monitoring, the patterns of signals, the patterns of the images we take are different from other applications. Like if it is a in biometric systems, if it is some pattern recognition applications, so in that case, the type of image or type of signal may be different uh, in a wide aspect from biomedical signals or images, right? So as I was discussing that why we are so much concerned about this particular domain of application, right? So the thing is that, yes, there are so many experts, the doctors having different domain expertise, right? Someone is experts in different neurological disorders, some others are experts in oncological, that is in cancer and something other else. Some others are really interested or expert in cardiovascular systems. So they are experts. Now the question comes, this field grows in such a way that when the doctor have some expertise on a certain domain, so they have an experience. That experience come from the observing different patients having different problems. So that bandwidth of different problems, actually how a doctor continuously observing a huge number of patients having different types of diseases, having different types of symptoms, gives the doctors a huge experience. And this experience are the main backbone of a very good treatment provided by the doctor. Because because if the doctor has a very good experience, he can have a good knowledge base. If he has a very good knowledge base, from that knowledge base he can identify the disease from different various types of symptoms, right? So there comes one aspect, that when this expertise is not there, when there is a lack of expertise, how we can address these issues? Another aspect is that even if I have an expertise, is that expertise is fully authenticated or fully that is, what should I say, that it is fully verified, that how we can become very much assured that it is absolutely correct? Because some disease, it is very important to identify the disease with high degree of accuracy. If it is fails to identify the disease with high degree of accuracy, in that case, the medication may be altered, and due to that medication, that patient may die. But the disease is not that much harmful that it may lead to that patient to die within a very small span. But because of because of inaccurate diagnosis, that happens, right? So in that cases, the doctors are very much concerned about the proper identification. So there comes different tools, different techniques that the doctors are trying to use different technological advancements in their field, so that they can make sure that yes, I have identified the disease with high degree of accuracy, right? So to achieve these, they have some different technological technological techniques that they can use, right? So some examples I will show you, then I will come to this image analysis part. Okay, so obviously these things, as I have told, that obviously why we are concerned about different vital parameters, why we are measuring or estimating different physiological parameters, different physiological changes we want to we need to estimate, we need to measure those values, because we need to identify, we need to monitor the disease, right? So as I have told that say an example of a skin lesion, let us consider an example of a skin lesion. So okay, so what happens, see, in this person has a lesson here, and that lesson, this is a basically a very a high definition digital image, a digital camera has been used, and that from that camera, that particular lesson can be identified, that can be observed by the physiologist or the doctors, right? And what is the purpose? Purpose is to identify whether there is any abnormality, yeah, in that particular lesion or not. If there is any abnormality, we need to go for different medications, right? So in that case, the doctor thinks that if can we have some other technology, so that I can have a much more detailed visualization, much more detailed information I can get from that particular lesson. So this image, you can see that this image tells you much detail about that particular lesson, which was not actually visible, or which was not actually accessible through this high definition digital image, camera image, right? So this particular image, you can see that how much detailed information it is providing. This information, this particular image is giving us an different changes of color, different changes of the uh, uh, that particular lesson shape, size, everything, right? In similar way, this is also a lesson, and that lesson, this is also a digital camera image. Doctors can have some visual inspection, can have some camera images for further analysis, but if this image is available to that doctor, it will give much more detailed visualization, much more detailed information regarding that particular lesson, right? So this type of technological development, their doctors are adopting to get the detailed visualization, to get more detailed information regarding that particular disease, right? And this particular imaging technique is called dermoscopic imaging, or and the instruments is called the dermoscope. So these are the dermoscopic images of different skin lesions, right? So now you can say that yes, so doctors, there was a problem. Problem was that we have a lesion, the patient have a lesion, and the doctors having some visual inspection, having expertise on that, he is trying to identify which disease it is, whether there is any abnormalities or not, trying to go for it, go with his expertise and the visual inspection, and also it may have some digital camera images. Now the doctor has this particular device or instrument. From that, it can take a much detailed information. It can acquire a different image of that particular lesion, which will give him a much detailed visualization, right? So problems solved? No, the problem actually arises from here. The problem is that when, if you very closely observe these images, you can see, even we are not an expert, even for an expert it may be a confusing, sometimes it become a confusing confusion for identifying or differentiating different diseases because of the similar appearance. You see, this image and that image have the same appearance, almost same color variations, presence of same color. Even in that particular two diseases, two lesions have the same color information, almost have same variations present. The structural shape of this particular lesion is almost similar to some extent to these lesions, right? So these things come into the picture. So when these things come into the picture, again the doctors try to identify the disease, even if they have a detailed visualization, detailed information, more information than the previous simple digital camera images. Even rather, it is much more detailing they are getting from visual inspection itself. Still, from these particular images, the doctors having a visual inspection and try to find out what are the different colors present, what are the different features that the doctor should look into, so that they can identify whether that particular lesion has any abnormalities, any specific disorder is there or not, right? So they are still dependent on the visual inspection, right? So sometimes these similarities, these color similarity, these textural similarities, the shape and structural similarities make the doctors confused about the proper diagnosis decision, to take a proper diagnostic decision, right? So in that case, can we help by analyzing those images to get a better understanding, to give a proper diagnosis with high degree of accuracy? Similarly, this is a very common images you have seen, that is the fundus image of eye. Most of the ophthalmologists use this particular imaging to identify whether there is any glaucoma present in the patient's eye, or whether there is any diabetic retinopathy, those who have the diabetes, right? So the thing is that uh, the identification is very important at the early stage, because if the glaucoma is not identified at the early stage, then it may lead to blindness. The patient may blind, right? So in that case, very significant regions the doctors need to be focused, right? Sometimes for diabetic retinopathy, doctors used to see the vessel structures, whether that vessels have the width of those vessels, the tortuosity of that vessels. If those vessels have different widths, the variation of widths will give the doctor an idea about the effect of diabetes into that patient's eyesight. Okay, for identification of glaucoma, doctors usually concentrate on this particular region, that is called the optic disc and cup region. Optic disc and cup region. So doctors identify the ratio between these optic discs and cup region. So how this disc and cup regions, the ratio between these two varies, that actually grade the glaucoma. This is a normal image for a normal glaucoma patient, and this is a highly affected patient with glaucoma, right? So there is basically the two regions. If you see, this bright portion has two regions. One is called the optic disc and another is called the optic cup. So optic disc and optic cup are basically overlapping regions. So sometimes it is very difficult to identify appropriately the optic disc and optic cup region, and then to identify or to determine the ratio between these two, how much area it is being covered by optic disc and optic curve. So here again the doctors are dependent on the visual inspection. So so can we make some contribution so that this inspection can be more easy and diagnosis can be better? See, this is the CT scan, high resolution CT scan of a lung. Okay, so from here you can see this is the left lung, this is the right lung, and this is a nodule. So what is the purpose? Purpose is that we need to identify whether there is any lung cancer or not. So before identifying the lung cancer, we need to identify whether there is any nodule or not. So if there is any nodule, we need to identify that yes, this is a nodule, and if it is a nodule, then what is the type of that nodule? What is the, whether it is a malignant or whether it is a benign nodule, right? So from these CT scan images, sorry, so from this CT scan images, you can see there will be lots of alveolus, alveoli, and some other objects will be there, and from there it will be difficult to identify whether there is a nodule present or not. And if that nodule is present, from a high resolution CT scan, it is sometimes very difficult to identify the characteristics of that particular nodule, to identify whether it is a malignant or benign nodule. Some examples are like that. See, in this particular image, this is the nodule, and this nodule is actually connected with the lung. You see, it is connected with the lung. So this feature, whether it is connected with that lung or it is not connected with the lung, this is one type of malignancy. So if it is connected with the lung, it is difficult, sometimes it is difficult to identify that whether there is a connection, whether it has been, it is joined with these two regions, the joint. Okay, so it gives a significant information, right? Similarly, if you see this particular image, there are few more number of circular or semicircular objects which may be interpreted as nodule, and these are basically are non-nodules basically, right? So there is no such nodules present in this particular CT scan image, which may or may not be that is, which may be identified as malignant or benign, right? So there is no, so first objective is to identify whether that is nodule or not. So when we have a visual screening, we sometimes fails to identify whether there is a nodule or not. If we have identified that nodules, sometimes we miss the important features to segregate that nodule or to identify that nodule as a malignant or benign, right? So this is also one important aspect. So what are the challenges? So these are the and some examples I have shown you to get some idea about where these image and signal processing tools can be applicable and why we are interested in that. So all those types of examples, we must have some challenges. That is, first challenge is the segregation of region of interest. As we have seen in the skin lesson, we need to identify the lesion area, because we have two terms, the diagnosis and monitoring. So to diagnose, for proper diagnosis, we need to observe, we need to estimate the structural properties of that lesion, whether that lesion is structurally similar, symmetric or asymmetric, whether there is any abrupt nature in the structure present or not, And if you come to the monitoring part, we need to monitor whether that lesson size is being increased or not. If it is increased, at within which duration, what duration it is being increased, whether it takes 6 months, whether it takes 3 months to get increased, or the size is not increasing, it is same as it is. So this is one monitoring part. So from this we can identify whether that is a cancerous lesion or not. Similarly, as we have discussed that for glaucoma identification, we need to identify the optic disc and cup region, and from that we need to determine the CDR, that is the cup disc ratio. So from that CDR we can identify or we can estimate whether what is the grade of that glaucoma. So for that also we need to segregate that region. We need to identify that particular region of interest, and then we have to determine that parameter. As in diabetic retinopathy, we need to determine the structure of vessels. We need to determine whether that vessels are what is the width of those vessels, what is the tortuosity of that vessels, right? So in that case we need to segregate that vessel structures. So this is in this case, this is the region of interest. Similarly, for lung CT images, we need to identify, we need to segregate that nodule. Then after segregating that nodule, we can identify whether that nodule is malignant or benign. So we need to develop segmentation algorithms. So first, the segmentation of RY, then detection of object, whether it is nodule or non-nodule. If it is nodule, then we can proceed further. If there is no nodule, then it is okay. So object detection is a very important part. That is, after segmenting that lung region, after extracting the lung region, there will be multiple objects, similar structures, and from that we need to identify among this is actually the true positive, that is the nodule is this, and if we have identified that nodule, if we can identify that object, then we can proceed whether based on that features whether that particular object is malignant or benign, right? Similarly, in case of diabetic retinopathy, there are some other objects present other than the vessel structures. What are those? Hard exudates, soft exudates. You can see these are the regions. You can see these are the regions. The brighter regions you can see. These are different objects that can give you an idea about the effect of diabetes in that patient's eye, right? So other than identifying the vessel structure, we can identify different objects present in that particular fundus image so that we can determine whether there is the diabetic retinopathy or not, right? So these are different hemorrhages is present or not, small red dots are present there or not, that we can identify from that particular fundus image to identify whether there is any diabetic retinopathy or not. Fine. So for that also we have a challenge to detect the objects. So after this segregation of the region of interest, object detection, the final challenge is the classification, the identification of the disease, the determination whether that disease is a that particular image is of a patient which have that particular problem or not. So there may be some different categories. It may be a binary classification problem, it may be multi-class classification problem, or it may be a subclass categorization of that particular class, right? So this for the skin lesions, we may have to identify whether that lesion is benign or malignant. Even we may need to identify some other classes, some other subcategories like malignant melanoma, nevus, BCC, and seborrheic keratosis. What is the purpose? Why we need this? Because some skin lesions which are actually non-malignant but have a potential to further convert into malignancy. Because of that, we need to identify, need to subcategorize that particular non-malignant lesions so that we can have an idea that if it is this, then there is a potential to again become a malignant lesion. So rather identify what category of this particular lesion is, right? Similarly, there obviously whether it is a normal or a diabetic retinopathy for that patient, and here we need to identify whether it is malignant or benign lung cancer image, right? So these are the challenges. So let us come to first problem, that is the computer aided skin disease monitoring system. So for that skin disease monitoring, we have the dermoscope. We have collected the dermoscopic images, done the image pre-processing so that we can deal with some artifacts present in that particular image. Then the segmentation to identify or to segregate the region of interest, identification of the border, and to extract some features, and then feature selection and classification to classify those images into different disease classes. So let us see how we can proceed. So first, I would like to discuss about a very simple image analysis tool, that is the mathematical morphology. Many of you may know, and I am giving just an overview of that. And I will try to discuss that how this particular tool can be explored, has been explored, so that different problems can be addressed. Different problems or different challenges can be addressed, and how this tool can be modified for different challenges, right? And some future aspects. So it is obviously a mathematical theory for analysis, and it is basically nothing but deals with the shape or morphology of the objects, right? And the fundamental element of mathematical morphology is called the structuring element, and this mathematics is actually defines the interaction between the image and the structuring element, and this interaction actually helps to segregate or to identify some specific objects, and that objects will be identified depending on their morphological properties, so that we can have an idea about the morphology of that particular objects, right? So yeah, so what is the structuring element? The structuring element is nothing but a combination of zeros and ones, and if it is a binary structuring element, if we consider, and the shape and size of the structuring element will depend on the shape and size of the object under consideration. Because the problem in the mathematical morphology is that, or the constraint of the mathematical morphology is that, there is no predefined rule or predefined guideline for the selection of the structuring element, right? So there may be different types of structuring element of different shape and different size, depending on the object under consideration, which object we are going to deal with, right? So we need to choose a proper structuring element so that we can deals with the morphological properties of that particular objects or the image under consideration. The fundamental operations of mathematical morphology are called the erosion and dilation, and these are nothing but the minimum and maximum operations, right? And this minimum and maximum operation is depends on how the structuring element is interacting with that particular image under consideration or the object under consideration, right? So if it is an image and this is my structuring element, then how, if this structuring element interacts with that input image, will give us, for a minimum operation, will give us an eroded image. Now see, this eroded image preserves the fundamental morphology of that particular object present in that particular image. Similarly, if we do the dilation operation, the same structuring element, using the same structuring element on the same image, the image will be dilated and preserving the fundamental morphology of that particular object present in that particular image, right? So how it works? So if we have an image like this is my original image and this is the structuring element, the fundamental, the terminology associated with dilation is the heat operation. That is, if I place the structuring element and if that structuring element interact and hit any of the pixels of that object, the center pixels of that coincide region will be replaced by the maximum value. So we can have that because this particular pixels has been coincide with the original image. The same way, if we move the structuring element further, we will see that it is still these two pixels are coinciding with the image pixels. So we can replace the center pixel with the maximum value. In the same way, we will get the dilated version of the original image. Now for erosion, the term became fit. Whether fit means that whether that structuring element is completely contained in that particular region or not. That is, if I place the structuring element in this particular location, you see that these pixels are not being, this structuring element, because of these pixels, is not being fully contained by that particular region of interest, right? So the center pixel will not be replaced by the minimum value. Similar way, if we move further, the complete structuring element is not coinciding or confined within that region of interest, right? So nothing will happen. Same way, if we place the structuring element in this location, this structuring element is completely contained by the region of interest, and then we can replace the center pixel by the minimum value, right? So in this way, we can get the eroded version of the original image, right? So these are the heat and fit terminologies associated with erosion and dilation. So these are some properties of erosion and dilation. I'm not going in detail. Now, this erosion and dilation, the combination of this erosion and dilation give us two more techniques. One is called opening and another is called closing. So closing is not, opening is nothing but the erosion followed by dilation, and the closing is dilation followed by erosion. So what happens if we perform the opening operation with a structuring element, that is consecutive operation of erosion and dilation? We can see that some objects, as the shape and size of the structuring element will be extracted, can be opened up, right? In the same way, if it is a closing operation, then some small regions compared to the size of the structuring element will be removed or closed by this operation. So the overall structure of the resultant image may vary. So in one operation, we can extract some regions, some operation we can remove some region, and obviously when we have such set of operation, using that set of operations we can make some morphological filters, and these morphological filters sometimes called the morphological gradient operation. That is, depending on the properties of those operations, we can design different filter to extract different information from that structure or the image, right? So first, in case of skin lesion identification, the first problem was the removal of hair artifacts, because in skin lesions, in human skin, there may be presence of some hairs, and those hairs may have some different widths, right? So for that, a morphological filter called morphological bottom hat filter has been used, right? In that morphological bottom hat filter, we have employed a circular structuring element of a very small size, because the hair-like structures may be considered as a straight line, but it may not be as a exactly straight line, but sometimes have some curvatures. So we can consider, we have, the thing is that we the idea behind this is that the selection of structuring element may be a circular structure, because we can have, we can, if we join a circle of points, we can get a straight line, even we can get any curve, right? So we have a small structuring element which will try to find out this particular hair-like structures. Even if the width varies, we can identify, we can segregate, we can extract those hair-like structures, and then we can remove those structures from the original image. After that, we can go for the segmentation and border detection. What is the purpose? Purpose is that the skin lesions usually widely varies in morphological properties. It may have different size, different shape, and the border may be irregular. The irregular structure is a significant information, is a significant feature towards the identification of malignancy, right? So we need to identify or need to segment the lesion area, and then we need to detect the border so that we can determine the irregularity present in that border, right? So again, the circular kernel as a structuring element has been chosen for the morphological operations. Why the circular kernel here? Most of the skin lesions either are oval in shape, circle in shape, right? Or we can consider it, or somehow we can approximate with a circle or an ellipse. But here we have choose a circle so that we can employ different morphological filters, right? So how we have determined, or how we have segment that lesion? We have a RGB image of that particular dermoscopic images of skin lesion, converted it into grayscale, and morphological closing operations has been performed with a circular structuring element having a little bit higher diameter of 8 pixels. So after the morphological closing operation, a morphological filtration has been performed by subtracting the complement of the original image from the closed image. And we can see that there is a distinct difference between the intensity of the region of interest and its background. So simple thresholding method can give you a very appropriate segmented image. This filtration actually helped us to make the distinction between the original, between the region of interest and the background, a distinct difference between the intensity. And choosing a that's why we have very choice of a threshold value become very easier, and we can get a segmented image. Now from that segment, on that segmented image, erosion operation has been performed by a little bit smaller structuring element of 4 diameter, circular structuring element. And then a morphological gradient operation has been performed by subtracting the eroded image from the segmented image, and we have determined the border of the segmented image. So after determining this segmented image and the border detected image, we can determine some morphological properties from that particular lessons. So these are some examples and how the segmentation performance has been evaluated. These are pixel level accuracy, sensitivity and specificity, and some other similarity based index, that is Jacquard similarity index and dice similarity coefficient has been evaluated. So this is a very common example I used to give, that this is a cartoon character. These are basically the cartoon characters, and we get some similarity between the original character, original personality, right? So how? Because nothing but by comparing different features, different information that may have similarity between the original personality and that particular cartoon character. So these are the basically the feature engineering. The feature engineering will give us that information which will lead us to identify the disease or identify that particular class very with high degree of accuracy, right? So for this particular problem, we may have different morphological features we can extract it. We extracted different texture features, and we can also have some color informations. So these are the different structural properties that has been extracted from the segmented and border detected images. So in the border detected image, you can see that some other border irregularity measurement technique has been discussed, that where we have an image, this is the border, and we need to determine how irregular this border is. So what we have done, from the centroid of that particular region of interest, we have determined the distance of each of the border pixels, and we can get a series, that is the pixel number and the distance to the centroid. And this series, from this series, we have determined the fractal dimension, Higuchi fractal dimension and Kahr's fractal dimension. These two fractal dimension estimation are usually employed, are usually used in time series data. So these two fractal estimation technique has been employed, and these two features has been considered to as a quantitative estimation of the irregularity of that particular border. Okay. Now another feature based technique has been used for the identification of multi-class skin abnormalities. Here what we have done, we have performed the cross correlation operation. You can see we have taken an RGB image and converted into different color spaces, and in each different color spaces we have 32 different kernels. I am coming to that part. And then each of that color space will be cross correlated with all those 32 kernels and will give us some features, and based on that feature we can identify what type of disease it is. That is the subclass categorization. So for this particular purpose, we have selected 4 disease classes, that is melanoma, nevus, BCC and seborrheic keratosis. Now you can see in these images some regions has been marked. These regions actually are very much important regions, are having very important features for that particular disease class, and these are being marked by a dermatologist who is our collaborator. He identified these particular regions by marking these regions. Okay, so for a particular disease class, say melanoma or malignant melanoma, in that class we may have different such features, and we have identified that we can have different type of features for different disease classes, and we compile all those features, selecting a set of images of different disease classes, and we make it as a 32 numbers features. That means we can say that for this particular region we have specific features, that is a very dark color, dark black regions. We can have some blue white veil region, or that is blue gray pigmentations. We can have some steel blue structureless area. All these regions has been selected as a very important features for different disease classes, and those regions has been selected as a kernel cropped from that particular images. That regions has been extracted right after the dermatologist has marked those regions. Now those kernels has been cross correlated with the original image of different different color spaces, right? And what we have got, we got the correlation coefficient, the cross correlation spectrum, where we can get the cross correlation coefficient. That means how much similar those regions, those features are, right, within that particular image, whether that particular image has those specific type of information present or not. So depending on that correlation coefficient, we have identified different regions in that particular four different disease classes, and from each of that regions we have extracted different histogram based features. Then from the cross correlogram we have determined the cross spectrum. The cross spectrum depicts the spectral similarity between the selected kernels, which are nothing but the features identified by the dermatologist, and the input image. So how close those features in spectral domain, how those features are close to each other, that can also be identified. That is, you can see that in this particular region, these peaks gives you the higher similarity in that spectral region. That means here the lowest frequency information have the higher similarity. Here you can see also the same, but in this case you can see the high frequency regions have the higher similarity. Okay, so from these we can take the spectral features. So there we have got the cross correlogram. Here we get the cross spectrum, and from cross spectrum we have determined the spectral features, right? And based on those features we have identified 4 different disease classes, that is malignant melanoma, nevus, BCC, and seborrheic keratosis. So after extracting different type of features, we can have different feature selection algorithm. Here I am going to discuss one feature selection algorithm that is called the recursive feature elimination based feature selection technique. That is the SVM RFE, SVM recursive feature elimination based feature selection technique. So we have extracted n number of features from each image, and then it is given to the SVM classifier, and depending on that weight value, that features has been made F1 to Fn features we have obtained from F1 to Fn previous features. The values has been assigned depending on the weight values. Now from that, the half of those features has been eliminated. In each iteration, those half of features has been eliminated, and depending on the elimination threshold value, we get a new feature set, and from that feature set we have the ranked features, like the feature which has been eliminated first has the lowest rank, and the feature which has been eliminated last has the highest rank. But the problem is that in this particular feature selection technique, we are eliminating half of those features at each iteration, right? And what happens? There may be we are eliminating some important features because they are correlated. Because of their correlation, some features are being eliminated which may have the potential to make the classification performance improve. So this technique has been improved, has been modified by introducing a correlation bias reduction technique, where after eliminating the half of those features, we have two feature set. One is existing feature set and another is eliminated feature set. Now in the eliminated feature set, we have determined a group threshold value and a correlation threshold value. In the what is that? In the group threshold value, we determine how many number of features we will consider in the elimination feature set, and correlation threshold value determines the correlation value, the correlation coefficient with the highest weight features. That is the feature which has the highest weight. The correlation with the other features with that particular highest value weight value feature will be determined, and we have, depending on the group threshold value, the group of features will be determined. And in that group of features, the features which is highly correlated with that highest weighted value will be selected, and that feature will be go back to the eliminate existing feature set. So the feature set now become fn by 2 plus 1, right? Now these features again will be used in the SVM classifier, and this way recursively we can determine a new feature set. That feature set are the rank feature set, where the feature which is eliminated first is the lowest rank feature, and the feature which has been eliminated last is the highest rank feature. So after this feature selection, feature extraction and feature selection, the multi-class classification has been performed. Here an ensemble model has been used. Why? Because as I have told that we need to identify the subcategory, subclass categorization, that whether that particular class has any potential to become malignancy, again recurrency is there or not, any chance of recurrency is there or not, right? And also we need to identify whether we have identified any disease, any skin lesion incorrectly in any such categories. If it is not, then it may not be within these 4 disease classes. That is, here we have chosen 4 disease classes depending on how severe these diseases are. That is, malignancy is one important, obviously an important disease class, and obviously the BCC and SK, these two also have some chances to become a malignant lesion. So because of that, we have considered these 4 disease classes. But sometimes some other disease class may be used or may be wrongly introduced in that particular model, and we must identify that class as others, that it should not be identified within that any 4 disease class, right? So that scope must be incorporated in that particular technique. So that's why we have used ensemble multi-level multi-class classification technique. So now thing is that doing when we are doing this research, we came across one thing, that it is in medical application, when we are doing anything, it must be justified or clinically correlated with the doctors. That means doctors must be convinced that these information, and because of these information, this particular disease has been identified as this disease class, and as this information is clinically correlated information, then only they will convinced and they will consider this tool or this model as a justifiable tool, or that can be used by the doctors in their day-to-day practice. To keeping these things in mind, we determine finally we came into that conclusion that we must incorporate the expertise of the doctors or the dermatologist, that they must have some techniques that they usually follow to identify whether that is a cancer or not, or whether this particular disease has any potential to recur as a malignant lesion, right? So to address this, we decided that let us introduce the experts' knowledge into our system, and we decided to make a expert system on the basis of the dermatologist's opinion, that how the dermatologists identify whether that image is of a cancerous lesion cell image or something else. So what is the fundamental? The fundamental is that the doctors or dermatologists usually follow the ABCD rule of dermoscopy, which is the gold standard rule. A for asymmetry, B for border, C for color, and D for dermoscopic structures. Now this asymmetry we can estimate, we can segment that image, we can identify the border, and we can get a numerical estimation of that irregularity. But whether it is clinically correlated, whether the doctors are convinced, how they are determining that asymmetry, they are also determining the asymmetry of that lesion. The border, whether that border is abnormal or not, whether the border is irregular or not, they also determine that. And these A, B, C, D all are numerical values. They quantify their visual inspection according to their own way to determine a score that is called the total dermoscopic score. And to determine this total dermoscope, after determining this total dermoscopic score, they identify whether that lesion is malignant or benign, or there is any suspicious lesion which may have that must be cross verified, or that lesion may have some potential to become a malignant lesion. Color, the C color is actually they determine by the presence of different types of colors. The dermoscopic structures, the presence of different dermoscopic structure is also one point. Another point is that how the dermoscopic structures are distributed in that lesion, whether that feature is global feature or whether that feature is a local feature, that they also identify from visual inspection. And we try to incorporate all those expertise into our system. Right? That's why we have make an expert system that is called the DERMEASY, a dermatological expert system, where some information we have collected from the dermatologists, we have developed some algorithms to get the segmentation, to get the border image, right? To extract different colors, to and then we make just exactly follow what they have done, what they usually do to identify, to determine those ABCD parameters, right? So this is the overall block diagram of the dermatological informatics module. Informatics module is nothing but where we are trying to determine that ABCD parameter values. So we have the dermoscopic image, right? And there is a lesson segmentation module. We employed any segmentation algorithm. We can develop any segmentation algorithm. Then the border detected image from that segmented image, color information has been extracted, and also the dermoscopic structures has also been identified. So after these four algorithms, we need to identify the asymmetry A from the segmented image, then the border irregularity, that color C. These all are the quantified value, quantitative value, A, B, C, D parameter values, right? And then based on those parameters, we have to determine the TDS, and then we have to generate, we have to finally make the decision whether it is malignant, benign, or any suspicious category. So in asymmetry analysis, the doctors scale this asymmetry between 0 to 2. That if there is no asymmetry, then it is 0. If the asymmetry is horizontally both the way, then it is 1, or vertically it is also 1. If it is both horizontally and vertically asymmetry, then it is 2, right? So for that, they also considered shape asymmetry, brightness asymmetry, and color asymmetry. That means here we have a segmented image, and that segmented image will be horizontally divided into two parts, and from that we have to identify whether these two halves have symmetricity or not. The same the doctors do from visual inspection. So how they have determined the shape asymmetry? The horizontal, and AV for vertical and AH for horizontal. So difference between this left and right for vertical, and for horizontal it is top and bottom difference divided by the entire area of that particular lesion. If it is greater than 0.02, that means if vertical asymmetry and horizontal asymmetry both are more than 0.02, then the asymmetricity will be high. If none of this is more than 0.02, then there will be no asymmetry. And if there is any one of these two is more than 0.02, then it will be close to 1. Now, before even after this vertical and horizontal asymmetry, that is the shape asymmetry, we have to consider the brightness asymmetry. Okay. Similarly, for brightness asymmetry, we need to determine that whether that brightness or the mean value of the pixel intensity difference between these two halves is whether it is more than 0.03 or not. And for color asymmetry, we have determined whether if there is nothing present in that, that is there is no shape asymmetry, no brightness asymmetry, no color asymmetry, then it will be 0. If it is shape, brightness, and color asymmetry is present, then this A will be 2. So in this case, the asymmetry has been scaled between 0 to 2 by considering all these three different types of asymmetry as that has been shown here, the rule base, and from that rule base, based on different combinations, it will be either 0, 1, or 2, and also in between either 0.25 or 0.5 or 1.25 or 1.5. For border irregularity, what doctors do, they subdivide that lesion border or the lesion into 8 sectors. If each of the sectors has an irregularity, then they will assign a value of 1. If none of the sector has an asymmetry, they will assign 0. So in this case, after getting that border image, we have determined the asymmetricity in each sector. If there is an asymmetry, then we assigned 1 for each sector. For color, they have considered 6 different colors, presence of 6 different colors. That is white, red, light brown, dark brown, blue gray, and black. So we have to identify that. Again, the dermatologist has marked different colors from a set of dermoscopic images. These are the different colors, and this color is black, that color is blue, that color is light brown, that is dark brown. All those 6 colors has been marked by the dermatologist, and we have generated the superpixel of each image, and from that we try to identify again in each superpixel whether that superpixel is close to any of those colors. And because of the presence of any of these colors, it has been scaled between 0 to 6. That none of this color is present, then it is 0. If all the colors present, then it is 6. Then the dermoscopic structure segmentation, right? So whether that structure is present or not, one point, and the next point, second point, is that how that structure is distributed, whether that structure is globally distributed or locally distributed. One feature, that is the dots and globules. So for the dots and globules identification, we have make the morphological filters having different size of structuring element. Okay, so we have the image and also we have the segmented image. So we have masked that image so that we should not identify any other objects from the normal skin region. Okay, then using the morphological filter, different objects has been identified, and depending on their area, we have extracted the dots and globules and identified the dots and globules from each of that image. Similarly, for a malignant and a non-malignant image. Now you can see in the malignant lesions, the globules will be much more dominating, and obviously the area covered by these dots and globules will be more compared to the non-malignant lesions, right? So this is the feature, this is the information the doctors look into, and we have quantified that whether the dots and globules present or not. If it is present, what is the area covered by that dots and globules in that particular lesion area. Then next is the pigment network. So pigment network is nothing but a net-like structure or an irregular mesh-like object, right? So for that, again, we have used the morphological bottom hat filter with linear structuring element and the bank of directional filter, so that we can get this pigment network. This is the pigment network we have identified from that particular lesson, and it has been superimposed on the original image. Now, if this pigment network is a globally distributed, then it is it signifies that this lesion is a non-malignant lesion. If that pigment network is a local feature, then it determines that there is a malignancy. Then next dermoscopic structure is called the structureless area. The structureless area is that area where the color or that texture will be almost same as the normal skin region. Okay, so in that case, we need to identify the structureless area. Again, some morphological filtering operations has been performed, and you see that from these particular images, we have this structureless area has been identified. Now, this structureless area, there also we have to determine what is the amount of area this structureless area is covered in that particular lesson. Next is the blue-white veil. This is also a color information. That color features this blue-white veil. It is a very critical feature. It may be present in malignant lesions or may be present in the non-malignant lesion. But if this blue-white veil is a global feature, then it is a non-malignant feature. If it is a local feature, then it is a malignant feature. So we need to identify the blue-white veil region and also the area covered by that region. Right now, yes. If the area covered by the dermatological structures, dermoscopic structures, is less than 0.1 of the area of that particular lesion, then it will be considered as an absent. If the structure is more than 0.1 and less than 0.5, that is the 10% to 50%, then it is a local structure. And if it is more than 50%, then it will be considered as a global structure. So now the rule base has been designed in such a way that whether that structuring element, or sorry, the dermoscopic structure is present in that particular lesion or not. If it is present, then what is the amount of area it is being covered, and what are the number of different structuring elements present, different dermoscopic structures present in that particular lesion, that also been identified. So depending on this, it has been, as we have considered 5 different dermoscopic structures, so it will be, it has been scaled between 0 to 5. So after determining these A, B, C and D parameters, we need to determine the total dermoscopic score. So if the total dermoscopic score is less than 4.75, then it will be considered as a benign lesion. If it is between 4.75 to 5.45, it is suspicious. If it is greater than 5.45, then it is malignant. Now these different values are also the gold standard values, and we just use these values to identify whether that lesion is malignant or benign categories. Okay. Next, how we compare, how we justified our system, we need to convince the dermatologist. So for each of that image, we have tested in that particular system must be cross verified by the expert. So here also, these are the features: the asymmetry, the border, C for color, all those colors, then D for dermatological structures or dermoscopic structures. We have cross verified by the experts. This is for the dermatological expert system developed by us. What are the findings, and here what the experts has determined. So this actually makes some justification so that we can convince the dermatologist. And this is the total dermoscopic score based categorization. How we have identified that lesion based on our TDS value and the TDS value which has been determined by the doctors and their categorization. So that is also been cross verified. So just I think I have more 10 minutes, right?
Yes sir, yes.
Yeah, okay. So this is the part of the skin disease identification. Now let me have an overview on the lung cancer identification part. So in case of lung cancer identification, as I have discussed, there will be few more stages and the challenge will be different for different type of images. Obviously in lung cancer identification from CT images, we have one major challenge to identify whether that is nodule or not. And if it is a nodule, then we have to identify whether it is a malignant or benign. So to achieve that, we need to follow some different stages. First stage, obviously the pre-processing, and then we need to segment the lung region, because in CT scan, it is not exactly separated, the lungs. Okay, so we need to segment that lung region. Then from that lung region, we need to identify the nodule candidate, whether that is nodule or non-nodule. So if it is a nodule, then we need to identify, need to classify whether it is malignant or benign. Now, in case of CT images, as you have seen in previous example, that we may have different objects having different shape and different structural properties, right? And throughout the skin lesion segmentation or through the skin lesion identification, whatever the objects we have seen, whatever the lung lesions we have, the skin lesions we have observed, most of all are basically a single object, and the structure of those objects, those lesions, are more or less similar. But in case of lung nodule detection, the problem is that all the objects, the nodule, non-nodule, there will be multiple objects, and maybe there have some similarities, right? So we need to identify which one is nodule and which one is non-nodule. So because of that, in previous example, previous case for skin lesion identification, we have considered a specific structuring element throughout the algorithm. But in this case, because of the variation of the different shape and size of the nodules or the objects present in the lung region, we have implemented the adaptive morphological filters. In that case, in the adaptive morphological filters, what we have done, we have changed the shape and size of the structuring element depending on some regional features, some local features present in that particular region. And we started with the fundamental structure we have considered as an ellipse. So ellipse will change its orientation and also the size, so that we can have a set of structuring element of different shape and size, and that's using that structuring elements we can employ different morphological operations, morphological filtration, so that we can extract different objects. These are the different mathematical expressions. I am not going through it because of time constraint. So how we can determine the semi-major axis, semi-minor axis, and the that is the orientation, so that we can have from this tensor. Then we can have different grayscale adaptive morphological operations that we have also discussed previously, that is the erosion, dilation, morphological closing and opening operations. And here you can see the different morphological structuring elements that we have obtained from by employing this adaptive technique, and we can see that how the size and shape of the structuring element has been varied. Now for the same way, we have employed the morphological filtration so that we can segment the lung region. Okay, so after the segmenting the lung region from this original CT scan image, we need to identify whether there is a nodule present or not. So there must be a nodule candidate detection algorithm, and from there we can identify whether it is a nodule or non-nodule from its morphological properties. So after determining the nodules or identifying that nodule, we can do the classification performance based on different features to identify whether it is malignant nodule or non-malignant nodule. So these are some segmentation performance that where we have different nodules and non-nodules objects, and we have segmented that And when we have segmented the nodule region and how these nodules are close to the ground truth images, that has also been estimated by different parameters, that is sensitive, pixel level sensitivity, specificity, accuracy, and the similarity indexes, so that we can uh, make sure that this segmented image or segmented nodule is close to the ground truth image. So this is the overall this I have tried to show you. My objective was to show you how a simple image analysis tool can be used and extended for different applications, for different at different stages, because there may not be only segmentation or some specific feature extraction application. There may be multiple applications, like as I have shown you in case of different dermoscopic structure segmentation. Here you can see different nodule and non-nodule detection, how a simple image analysis tool can be extended and can be used in different applications. And now many deep learning and advanced techniques are being used for the segmentation purposes and that classification purpose. The this particular discussion may lead you or may give you some idea about that how this image analysis techniques, how these image analysis tools can be incorporated in the deep learning based techniques. Because when we are talking about the medical image analysis, when we are talking about the diagnosis, we need to convince the doctors, we need to convince by showing that these are the clinically correlated features we are extracting. It is not like that we are giving an image, a system is there, a particular model is there, and we are getting some results, we are getting a very good results. It may not be sufficient to convince the doctors and to use that system in their day-to-day practice. Okay, so these are the things, and we can also explore these different tools for different other imaging techniques, other imaging modalities. So and also and uniform model can be developed which can be used for different imaging techniques for different applications. That can also be future scope of research. Okay, so these are the few takeaway points from my today's discussion, and I should acknowledge some of my collaborators, Professor Munshi and Professor De, Dr. Gorai, for as he's a dermatologist in Apollo Gleneagles Hospital, Kolkata, and obviously Dr. Amitabh Haldar. This is the book. You can get it from Amazon. That is on skin disease identification, and that's all from my side. Thank you all.
Thank you, sir. It was a great lecture, sir. You have covered and explained everything very clearly. Any questions?
If there is any question, you can ask.
Okay, sir. Thank you, sir, once again for your valuable contribution. Thank you so much.
Thank you. So if
yes,
you
sir.
are interested to any collaboration,
yes, sir. In the future also, yes, sir. I am also planning the same, sir.
Yes. So I am always ready for it. And
yes,
if any participants or any students of IIIT Kottayam is interested to do PhD, they can also contact directly to me, and the PhD admission notification has been there in the IIT Rourkela website, so you can also go through it, and you can directly contact me if you are interested. So
yes, sir.
yeah. Okay.
Thank
And
you, sir.
thank you so much for giving me an opportunity to interact with you.
So it is a really great lecture, sir. You have explained very clearly, sir. I think uh, they are not. I think they don't have any questions, sir. I think. Shall we stop, sir? Here?
Yeah, thank you so much.
Yes, thank you, sir.